Hello fellow Sapiens and welcome to Prehistoric World. Take a moment to settle yourself. Maybe you're preparing to sleep. Maybe you're cooking, showering or working with headphones on. Perhaps you're walking through city streets or sitting in a quiet room, searching for something to occupy your mind during these late hours. Whatever brought you here tonight, you've arrived at the right place for a journey through deep time, a journey that will take us to places and times so alien that they challenge our most fundamental assumptions about what it means to be alive. Before we begin, I want to ask you to hit that like button and subscribe if you haven't already. It truly helps this type of content reach more people who might need exactly this kind of exploration into our planet's ancient mysteries. These stories of deep time, of prehistoric worlds, of evolutionary horror and wonder, they deserve to find their way to curious minds around the globe. And I'm genuinely curious about you, the person listening to this right now. How do you use this channel? Are you here to fall asleep letting these ancient stories carry you into dreams of deep time? Are you studying, using these narratives to understand the vast sweep of evolutionary history? Are you working late, needing something to occupy the analytical part of your mind while your hands stay busy? Or are you simply someone who finds peace in contemplating the immensity of geological time, the way others find comfort in looking at stars? And from where in the world are you listening? Are you in a bustling city, surrounded by the artifacts of human civilization while we explore times before consciousness existed? Are you in a quiet rural area, perhaps closer to the kind of landscapes where these ancient dramas played out? Are you in the southern hemisphere, where some of our best fossil evidence comes from, or in the north, where ice ages preserved clues about more recent prehistoric worlds? Drop a comment and let me know. I read every single one, and your stories of how and why you listen help me understand what these explorations mean to people. You'll find timestamps in the description for those of you who prefer to jump around, who want to revisit particular chapters or skip to specific time periods. But this is a story that's best experienced from beginning to end, because what we're building together isn't just a series of disconnected facts about ancient life. It's a narrative, a carefully constructed journey through the most terrifying and magnificent periods in Earth's history. Each chapter builds on the last, weaving together themes of evolution, extinction, adaptation, and survival that span not just hundreds of millions of years, but billions. Tonight we're going to explore a question that haunts paleontologists and keeps evolutionary biologists awake at night. What made the Earth before dinosaurs so terrifying that it makes our worst nightmares seem tame? We're talking about a world so alien, so hostile, so utterly foreign to anything we know today, that it challenges our very understanding of what it means for life to exist on this planet. But here's what makes this exploration different from typical discussions of prehistoric life. We're not just going to catalogue strange creatures or bizarre ecosystems. We're going to understand why these ancient worlds were terrifying in ways that go far beyond simple physical danger. We're going to explore how the very foundations of biology, chemistry and physics created conditions that would be literally unimaginable to modern life. It is strange to imagine, but there was a time when our Earth was a place where nightmares lived and breathed, where the very air could kill you in seconds, where creatures existed that were so bizarre they seemed pulled from the deepest corners of science fiction, where the ocean itself was a toxic soup that would dissolve your body, where the sky burned with colours that no human eye has ever seen, where the ground beneath your feet was alive with horrors that make our modern concept of predation look gentle by comparison. And yet, this wasn't fiction. This wasn't the product of some fevered imagination or Hollywood special effects team. This was home. This was Earth. This was the crucible that forged everything that came after, including the very neurons in your brain that are processing these words right now. The honest answer is that what we're about to explore together might change how you see everything around you. The ground beneath your feet, the air you breathe, the other living things that share your world, and most importantly, the incredible, improbable, nearly impossible journey that led to this very moment of your existence. We're going to discover that the history of life on Earth isn't a gentle progression from simple to complex, from primitive to advanced. It's a story of repeated catastrophes, evolutionary arms races, and survival strategies so extreme that they redefined what it means to be alive. It's a story where the heroes are often indistinguishable from the monsters, where survival required becoming something terrible, and where the line between predator and prey was written in chemistry, physics, and blood. So settle in, fellow Sapiens. We have billions of years to cover, and every single one of them was more terrifying and more wonderful than you might imagine. Chapter 1: The World Without Oxygen. The world without oxygen. There is a moment in Earth's early history around 3.8 billion years ago that would have killed you in seconds. Not from cold, not from heat, not from predators, but simply from trying to breathe. This wasn't a world that was merely hostile to human life. It was a world where the very concept of breathing, as we understand it, was not just impossible, but deadly. Imagine a time when the very act of taking a breath would have been lethal. The atmosphere contained virtually no oxygen, less than 0.001% compared to today's 21%. To put this in perspective, modern climbers on Mount Everest breathe air that contains more oxygen than the entire early Earth atmosphere. But the absence of oxygen was just the beginning of the horror. Instead, the air was thick with methane, ammonia, hydrogen sulfide, and carbon dioxide. The smell alone would have been overwhelming. Rotten eggs mixed with the acrid burn of volcanic gases, the sharp chemical tang of ammonia, and the suffocating weight of carbon dioxide so concentrated it would have felt like drowning in invisible liquid. This was a cocktail of poison that blanketed the entire planet, from sea level to the highest elevations. Recent atmospheric modelling suggests that methane concentrations may have been 100 to 1,000 times higher than today's levels. Hydrogen sulfide, the gas that gives rotten eggs their distinctive odour, was so abundant that it would have been detectable not just in the air, but dissolved in the oceans, creating a global environment that was essentially one vast planet-sized chemical weapon. But here's the twist that makes this ancient atmosphere even more terrifying. This toxic cocktail wasn't just a side effect of an unformed world, it was being actively maintained by life itself. The dominant organisms of the time, methanogens and other archaea, actually produced these poisonous gases as waste products. Life was literally creating an environment that would be deadly to almost every form of life we know today. Think about that for a moment. The very first successful life forms on Earth were organisms whose basic metabolic processes produced waste that would kill you instantly. They weren't just surviving in a toxic world, they were creating it, maintaining it, and thriving in it. It's as if the first chapter of life's story was written by organisms whose very existence was an act of chemical warfare against the future. We cannot know for certain, but evidence suggests that hydrogen sulfide concentrations were so high that the sky itself may have appeared orange or brown rather than blue. The physics of light scattering through such a dense chemical haze would have created sunsets and sunrises of colours that no human eye has ever seen. Brilliant oranges, deep purples, and sickly yellows that would have painted the entire world in the palette of a fever dream. Picture trying to see through a perpetual haze of industrial smog, but knowing that this pollution was natural, created by the very foundations of biology. Visibility would have been limited to perhaps a few hundred meters at best. The air would have shimmered with chemical heat, creating optical illusions and distortions that would have made navigation by sight nearly impossible, if there had been any complex organisms capable of sight to begin with. The haunting question is, how did life not just survive, but thrive in these conditions? The answer lies in understanding that our modern definition of livable is incredibly narrow, shaped by billions of years of evolutionary history that has adapted us to a very specific set of chemical conditions. These ancient organisms, our earliest ancestors, found ways to extract energy from chemical reactions that would dissolve your lungs before you could even feel pain. Scientists have found evidence of these ancient atmospheres trapped in mineral formations, preserved like messages from a toxic past. The isotope ratios in ancient rocks, particularly in formations like the Pilbara Craton in Western Australia and the Barberton Greenstone Belt in South Africa, tell us that methane levels were potentially overwhelming by modern standards. These ancient rocks contain mineral signatures that could only have formed in the presence of specific atmospheric gases. Sulfur isotopes in particular preserve a record of atmospheric chemistry going back billions of years. The ratios we find in rocks from this period tell a story of an atmosphere so chemically different from our own that it might as well have belonged to an alien planet. To put this in perspective, if you could somehow transport the atmosphere of 3.8 billion years ago to modern Earth, it would create a greenhouse effect so intense that our oceans would boil away within decades. The thermal properties of methane and carbon dioxide in such concentrations would trap solar radiation so efficiently that surface temperatures would skyrocket beyond the survival limits of any known life form except the most extreme thermophiles. The reveal is that this wasn't just a brief phase in Earth's development, some unfortunate accident of planetary formation that was quickly corrected. This toxic atmosphere persisted for over 1 billion years, a stretch of time so vast that it's difficult to comprehend. If Earth's entire history were compressed into a single year, this period of atmospheric poison would last from January until April. If human civilization were represented by the last second of December 31st, this toxic atmosphere would represent the first third of the entire year. During this billion-year reign of chemical terror, entire continents were shaped and reshaped. Mountain ranges rose and fell, asteroid impacts scarred the surface. The moon was significantly closer, creating tides that would dwarf anything in recorded history. And through it all, the atmosphere remained a toxic fog that would have been instantly fatal to any form of complex life. And yet, beneath those toxic skies, in the depths of ancient oceans that were more like chemical soup than water, something revolutionary was beginning to happen. Microscopic organisms were developing a new trick, one that would eventually transform not just the atmosphere, but the very nature of life itself. They were learning to harness the energy of sunlight directly, through a process that would eventually be called photosynthesis. But here's where the story becomes truly haunting. The organisms that would eventually save the planet from this toxic atmosphere would do so by creating what many scientists call the first mass extinction event in Earth's history. The cure, as we'll see, would prove to be deadlier than the disease, more catastrophic than the poison it replaced. These early photosynthetic organisms, the cyanobacteria, were essentially biological pollution control devices. But their method of cleaning up the atmosphere involved producing a waste product that was even more toxic to existing life than the gases they were removing. They were environmental saviors and environmental destroyers simultaneously, depending on your perspective and your biochemistry. The waste product they produced, oxygen, would eventually become the foundation of all complex life on Earth. But to the organisms that had spent billions of years perfecting life in a methane and sulfide world, oxygen was as deadly as cyanide gas. More deadly, actually, because cyanide merely stops cellular respiration, while oxygen actively destroys cellular structures through oxidation. So the question remains, if this toxic world was so perfectly suited to the life that created it, what force was powerful enough to destroy this ancient equilibrium? And why should we be grateful that it did, even though it killed nearly everything alive at the time? The answer lies in understanding that evolution doesn't care about individuals, or even species. It cares only about the continuation of information, and sometimes the best way to preserve that information is to destroy the very systems that created it. But before we can understand the forces that would eventually transform this toxic world, we need to appreciate just how perfectly adapted life had become to these seemingly impossible conditions. The organisms that thrived in Earth's earliest atmosphere weren't struggling survivors clinging to existence in a hostile world. They were supremely successful, highly sophisticated biological systems that had turned environmental poison into evolutionary advantage. Recent advances in molecular biology have allowed scientists to study modern descendants of these ancient organisms, archaea that still live in extreme environments around the world. What they've discovered is remarkable. These organisms don't just tolerate conditions that would be instantly fatal to most modern life. They require them. They have biochemical pathways so fundamentally different from familiar biology that they seem almost alien in their sophistication. The methanogens, for instance, don't just produce methane as a waste product. They use the chemical energy released in methane production to power their metabolism. They have essentially turned what we consider pollution into food. Their cellular machinery includes enzymes that can only function in oxygen-free environments, and exposure to even small amounts of oxygen causes immediate and catastrophic cellular damage. Recent research has revealed that some of these ancient organisms developed what we might call chemical warfare capabilities that went far beyond simple methane production. They could synthesize complex organic compounds that were toxic to competing organisms, essentially poisoning their environment to eliminate competition while remaining immune to their own chemical weapons. These weren't simple, primitive organisms fumbling their way toward more complex life. They were biochemical masters of their environment, with metabolic pathways of stunning sophistication and efficiency. Some could extract energy from the simple combination of hydrogen and carbon dioxide, turning the most basic atmospheric components into the fuel for life. Others developed the ability to use sulfur compounds in ways that created elaborate chemical cycles, transforming the ocean's chemistry to suit their metabolic needs. The evidence for their success is overwhelming. For over 1 billion years, a period longer than the entire history of complex multicellular life, these organisms dominated Earth's biosphere. They shaped the chemistry of the oceans, determined the composition of the atmosphere, and created geological formations that we can still see today. Recent analysis of ancient microbial mats preserved in rock formations has revealed ecosystems of extraordinary complexity. These weren't just random collections of simple cells, but organized communities with sophisticated division of labor, chemical communication systems, and even primitive forms of cooperation and competition. Some formations preserve evidence of what appear to be the first biological cities, massive microbial structures where different species of archaea work together to create environments that were optimal for their collective survival. These structures could extend for kilometers across ancient sea floors, creating three-dimensional biological architectures that modified water flow, concentrated nutrients, and created specialized microenvironments within the larger toxic atmosphere. The chemistry of these ancient ecosystems was so different from anything in the modern world that it challenges our basic assumptions about what life requires. Instead of oxygen-based respiration, these organisms used chemical pathways that extracted energy from hydrogen sulfide, methane, and other compounds that are deadly poisons to modern life. But perhaps most remarkably, they had developed biological technologies that wouldn't be reinvented until billions of years later. Some ancient archaea developed the ability to produce complex organic polymers, essentially biological plastics, that they used for structural materials and protective coatings. Others created sophisticated chemical sensors that allowed them to detect and respond to environmental changes with precision that rivals modern biological systems. Recent discoveries have revealed that some of these organisms were capable of what we might call environmental engineering on a global scale. They didn't just respond to their environment, they actively modified it to create conditions that were optimal for their survival and reproduction. The sulfur cycle, which is still one of the most important geochemical processes on Earth, was essentially created by these ancient organisms. They developed metabolic pathways that could transform sulfur compounds in ways that created vast deposits of sulfur-containing minerals, many of which are still mined today for industrial purposes. The carbon cycle, which regulates Earth's climate and atmospheric composition, was similarly shaped by ancient microbial communities. These organisms learned to manipulate carbon compounds in ways that could store vast amounts of atmospheric carbon in geological formations, creating some of the earliest forms of biological climate control. And yet, for all their success and sophistication, these ancient masters of the toxic Earth carried within their very biology the seeds of their own destruction. The chemical pathways that made them so successful in methane-rich, oxygen-free environments also made them extraordinarily vulnerable to any change in atmospheric composition. Their cellular machinery was so perfectly adapted to specific chemical conditions that even small deviations could cause catastrophic system failures. They were like precision instruments calibrated for one specific task, incredibly effective under the right conditions, but completely useless when those conditions changed. Recent molecular analysis has revealed that many of these ancient organisms lacked the genetic flexibility to adapt rapidly to environmental change. Their DNA repair systems, while adequate for their stable chemical environment, couldn't cope with the kinds of molecular damage that would be caused by exposure to oxygen or other atmospheric changes. More critically, their metabolic pathways were so interdependent that disruption of any single component could cause the entire system to collapse. They had evolved such efficient specialization that they had lost the metabolic flexibility that might have allowed them to survive in different chemical environments. This biological perfection, this exquisite adaptation to their toxic world, would prove to be their fatal weakness when the first photosynthetic organisms began to change the fundamental chemistry of Earth's atmosphere. The very efficiency that had made them masters of the Archean Earth would make them helpless victims of the oxygen apocalypse that was about to begin. The stage was set for one of the most dramatic transformations in Earth's history, a planetary catastrophe that would end billions of years of successful evolution and create the conditions necessary for everything that would follow, including the chain of events that would eventually lead to your existence as you listen to these words tonight. Chapter 2: The Great Oxidation, the Oxygen Apocalypse. Around 2.4 billion years ago, something began to happen that would make every previous catastrophe in Earth's history look like a minor inconvenience. It started slowly, almost imperceptibly, in scattered colonies of microscopic organisms that had developed what seemed like a clever new way to gather energy. But what emerged was an extinction event so complete, so devastating, that it wiped out the majority of life on Earth and fundamentally restructured the chemistry of the entire planet. The killer? Oxygen. The very gas that keeps you alive as you listen to these words. It is strange to imagine, but the substance that you're breathing right now, the molecule that your cells are using to extract energy from food, the gas that enables your brain to process these concepts, was once the most toxic pollutant our planet had ever known. To the organisms that had ruled Earth for over 1 billion years, oxygen was as deadly as chlorine gas is to you. More deadly, actually, because chlorine simply burns tissue, while oxygen attacks the fundamental chemistry of life itself. The evidence for this ancient catastrophe is fragmentary, but what we can piece together tells a story of unprecedented biological warfare. The perpetrators were cyanobacteria, tiny blue-green organisms not much larger than the period at the end of this sentence. They developed photosynthesis, a process that seemed almost magical, converting sunlight, water, and carbon dioxide into energy, and releasing oxygen as a seemingly harmless waste product. But nothing in evolution is truly harmless. Every innovation has consequences, every advantage comes at a cost, and every solution creates new problems. The cyanobacteria's solution to the energy problem was elegant and efficient, but its consequences would be catastrophic beyond imagination. At first, the ancient ocean absorbed this oxygen through chemical reactions with dissolved iron. This created vast bands of red iron oxide, rust essentially, that we can still see in rock formations today. These banded iron formations are found on every continent, from the Lake Superior region of North America to the Pilbara region of Western Australia. They're like geological crime scene photos, showing us exactly when and where this atmospheric revolution began. The bands themselves tell a story of cycling atmospheric chemistry. Red bands, rich in oxidized iron, alternate with darker bands of reduced minerals, suggesting that oxygen production wasn't constant but fluctuated over time. Perhaps cyanobacterial populations waxed and waned with seasonal changes, or with availability of nutrients. Perhaps there were early mass die-offs as the cyanobacteria struggled to adapt to their own waste product. Recent research has revealed that these banded iron formations aren't just simple geological structures, they're complex records of early biological activity. The thickness of individual bands, the ratios of different iron minerals, and the presence of trace elements all provide clues about the biological and chemical processes that created them. But here's the twist that makes this story even more dramatic. The ocean's ability to absorb oxygen wasn't infinite. For perhaps hundreds of millions of years, the seas acted like a vast chemical sponge, soaking up the oxygen that cyanobacteria produced and converting it into harmless rust. But around 2.4 billion years ago, the system reached a tipping point. The iron was exhausted. The ocean's capacity to absorb oxygen was finally overwhelmed, and for the first time in Earth's history, oxygen began to accumulate in the atmosphere as a free gas. What had been a minor waste product became an unstoppable force of environmental destruction. The honest answer is that we're still discovering the full scale of this catastrophe. Recent research suggests that oxygen levels didn't rise gradually, as once thought, but in dramatic pulses that may have reached concentrations far higher than modern levels. Some estimates suggest that atmospheric oxygen may have spiked to as high as 35% of the atmosphere, nearly twice what we breathe today. This created conditions so oxidizing that organic molecules would spontaneously combust. The very chemistry of life was under attack. Imagine a world where the air itself was flammable, where lightning strikes would ignite atmospheric fires that could burn for days, where any organic compound exposed to air would begin to break down immediately, not through biological decay but through direct chemical attack. For the methanogens and other anaerobic organisms that had dominated Earth for billions of years, oxygen was like acid rain falling from the sky 24 hours a day. It destroyed their cell walls, interfered with their metabolism, and created toxic byproducts that poisoned them from within. The proteins that had evolved over billions of years to function in an oxygen-free environment were suddenly encountering a chemical that could unravel their molecular structure in minutes. Entire ecosystems collapsed. The geological record shows a dramatic reduction in the diversity of mineral formations that anaerobic organisms had created. Stromatolites, layered structures built by ancient microbial communities, show clear evidence of mass die-offs during this period. Where once these biological communities had thrived across shallow seas worldwide, they suddenly became rare and restricted to a few isolated environments. We cannot know for certain, but some scientists estimate that up to 99% of all life on Earth may have died during the Great Oxidation event. To put this in perspective, this was a more complete extinction than the one that killed the dinosaurs. It was genocide on a planetary scale, carried out by the waste products of photosynthesis. The scale of this devastation is almost impossible to comprehend. Imagine every ecosystem on Earth, from the deepest ocean trenches to the highest mountain peaks, suddenly becoming uninhabitable. Imagine the chemistry of the entire planet changing so dramatically that 99 out of every 100 living organisms simply couldn't exist anymore. And yet the haunting question that lingers is this: why do we call this catastrophe the Great Oxidation event instead of the Great Dying? Why do we speak of it as a breakthrough rather than a disaster? Because hidden within this apocalypse was the key to everything that would come after. The organisms that survived, that found ways to not just tolerate oxygen but to use it, discovered something extraordinary. Oxygen-based metabolism is incredibly efficient compared to the anaerobic processes that had dominated early Earth. Where anaerobic organisms might extract a few molecules of energy from their food, aerobic organisms could extract dozens. It was like discovering fire or the wheel or electricity, a fundamental breakthrough that changed the rules of what life could accomplish. This efficiency advantage was so overwhelming that it would eventually lead to the evolution of complex cells, multicellular organisms, intelligence, and ultimately consciousness itself. Every thought you think, every movement you make, every heartbeat that keeps you alive depends on the efficient extraction of energy from food using oxygen-based metabolism. But the story doesn't end with survival and adaptation. The Great Oxidation event created conditions that would lead to something even more extraordinary and terrifying. The first complex cells with sophisticated internal structures, and eventually the first true predators, organisms that looked at other living things and saw not neighbours, but food. The survivors of the oxygen apocalypse weren't just biochemically different from their predecessors. They were fundamentally more complex, more capable, and more dangerous. They had access to energy levels that could support larger sizes, faster metabolisms, and more sophisticated behaviours than anything that had existed in the anaerobic world. So the question remains, if oxygen was deadly enough to cause the most complete mass extinction in Earth's history, what other changes did it trigger that made the ancient Earth even more dangerous than before? The answer lies in understanding that the Great Oxidation event didn't just kill the old world, it gave birth to a new one, populated by organisms with capabilities that would have seemed impossible in the age of methane and hydrogen sulfide. But to truly comprehend the magnitude of this transformation, we need to understand that the Great Oxidation event wasn't a single catastrophe. It was a cascade of interconnected disasters that unfolded over tens of millions of years, each more devastating than the last. Recent geochemical analysis has revealed that the transition from an oxygen-free to an oxygen-rich world happened in at least 3 distinct phases, each marking a new level of atmospheric toxicity that eliminated different groups of organisms. The first phase, beginning around 2.45 billion years ago, saw oxygen levels rise from essentially 0 to perhaps 0.1% of atmospheric composition. This seems like a tiny amount, but for organisms that had never encountered free oxygen in their billions of years of evolution, even this trace concentration was catastrophic. Recent analysis of ancient soil deposits from this period shows evidence of massive biological die-offs, layers of organic matter that accumulated faster than they could decay, suggesting that entire ecosystems were collapsing simultaneously. During this first phase, the most oxygen-sensitive organisms disappeared almost immediately. These were the extreme anaerobes, organisms so adapted to oxygen-free conditions that even molecular traces of oxygen were instantly lethal. Recent molecular analysis of their modern descendants suggests that these ancient organisms had biochemical pathways so finely tuned to anaerobic conditions that exposure to oxygen caused immediate and irreversible protein denaturation. The second phase, occurring around 2.3 billion years ago, saw oxygen levels spike to between 1 and 5% of atmospheric composition. This was the phase that eliminated most of the methanogens and other archaea that had dominated Earth for over 1 billion years. But it also created something unprecedented in Earth's history: the first widespread biological arms race between oxygen producers and oxygen detoxifiers. Recent research has revealed that some organisms didn't simply die during the Great Oxidation event, they fought back. They evolved increasingly sophisticated mechanisms for neutralizing oxygen before it could damage their cellular machinery. Some developed primitive antioxidant systems, chemical compounds that could absorb oxygen and render it harmless. Others evolved cellular compartments where they could sequester oxygen away from their most sensitive metabolic processes. But perhaps most remarkably, some organisms began to develop what we might call oxygen warfare capabilities. They learned to produce reactive oxygen species, highly toxic forms of oxygen that were even more deadly than the regular oxygen accumulating in the atmosphere. These biological weapons were used to attack competing organisms, essentially turning the environmental catastrophe into an opportunity for biological warfare. The fossil record from this period preserves evidence of what paleontologists call chemical battlefields, sedimentary layers where different microbial communities appear to have engaged in sustained chemical warfare using various oxygen-based toxins. These ancient conflict zones show clear evidence of offensive and defensive strategies, with some organisms developing chemical shields, while others evolved increasingly potent oxygen-based weapons. The third and most devastating phase began around 2.1 billion years ago, when oxygen levels reached concentrations that were toxic, even to organisms that had managed to survive the earlier phases. This was when atmospheric oxygen concentrations may have exceeded modern levels, creating conditions so oxidizing that they threatened even the newly evolved oxygen-tolerant organisms. Recent atmospheric modelling has revealed that during this phase, the Earth's atmosphere became a global combustion hazard. Lightning strikes could ignite methane-oxygen mixtures, creating atmospheric fires that burned across continents. Volcanic eruptions could trigger explosive reactions between volcanic gases and the oxygen-rich atmosphere, creating blast effects that were orders of magnitude more powerful than anything we see in modern volcanic activity. The geological record preserves evidence of these atmospheric fires in the form of widespread carbon deposits that could only have formed through massive combustion events. Some formations suggest that entire continents may have been swept by fires that burned not just surface vegetation, but organic matter buried meters deep in sediments. But the most haunting aspect of this atmospheric transformation wasn't the direct toxicity of oxygen. It was how oxygen changed the fundamental rules of biological competition. For billions of years, life had been primarily cooperative. Organisms competed for resources, but they rarely actively hunted and killed each other for food. The energy requirements for such behaviour were simply too high given the inefficient metabolic processes available in the oxygen-free world. Oxygen changed everything. The efficiency of aerobic metabolism was so much higher than anaerobic processes that it suddenly became energetically feasible for organisms to invest energy in hunting, killing, and consuming other organisms. For the first time in Earth's history, it made biological sense to be a predator. Recent analysis of early eukaryotic fossils, the first complex cells with internal structures, has revealed that many of the earliest complex organisms were predators. They had evolved specialized cellular machinery for capturing, immobilizing, and digesting other cells. This was unprecedented in the history of life and represents one of the most significant behavioral innovations in evolutionary history. These early predators weren't just larger or stronger than their prey. They were fundamentally different types of organisms. They had evolved active metabolisms that allowed them to move rapidly through their environment in search of prey. They had developed sensory systems that could detect potential victims from considerable distances. Most importantly, they had evolved the ability to make decisions about which organisms to attack and which to avoid. Recent research has revealed that the evolution of predation during the post-oxidation world wasn't gradual. It was explosively rapid. Within perhaps a few million years of the final oxygen crisis, marine environments were populated by sophisticated cellular predators with hunting capabilities that approached those of modern single-celled organisms. These early predators created evolutionary pressures that had never existed before. For the first time, organisms had to worry not just about finding food and avoiding environmental hazards, but about not becoming food for other organisms. This drove the evolution of the first biological defenses specifically designed to resist predation: cell walls, protective shells, chemical toxins, and evasive behaviors. The arms race between these early predators and their prey would become one of the most important driving forces in evolution, pushing organisms to become larger, faster, smarter, and more sophisticated in ways that would eventually lead to the complex ecosystems we know today. And yet, even as this new oxygen-rich world was proving deadly to the ancient masters of Earth, it was also creating opportunities for evolutionary innovations that would have been impossible in the old anaerobic environment. The energy abundance provided by aerobic metabolism wasn't just making predation possible, it was making complexity possible on scales that had never existed before. The stage was set for the evolution of the first truly complex cells, and eventually the first organisms that would hunt, not just with chemical weapons or simple engulfment, but with intelligence, strategy, and capabilities that would transform Earth into a world of sophisticated biological warfare. Chapter 3: The First Hunters. The birth of predation. There is a moment, roughly 1.8 billion years ago, when something unprecedented happened in Earth's oceans. For the first time in the planet's history, one living thing looked at another living thing and saw not a neighbour, but a meal. Before this moment, life had been surprisingly cooperative. Organisms competed for resources, certainly, but they didn't actively hunt and kill each other for food. The earliest life forms were content to absorb nutrients from their environment, break down organic matter, or harness energy from chemical reactions. They were, in essence, the world's first vegetarians, though in a world without plants. The evidence suggests that the first predators were microscopic, but their impact was anything but small. These weren't the dramatic hunters we might imagine. There were no chase scenes, no dramatic struggles. Instead, these early predators simply engulfed their prey whole, like cellular Pac-Man games playing out in ancient seas. But here's the twist. The evolution of predation didn't just add a new character to life's story, it completely rewrote the rules. Suddenly, being alive wasn't just about finding food and reproducing, it was about not becoming food for something else. This triggered what scientists call an evolutionary arms race. Prey organisms began developing defenses: thicker cell walls, toxic chemicals, better camouflage, faster movement. Predators responded by developing better weapons, more efficient hunting strategies, stronger digestive systems, improved sensory abilities. The reveal is that this arms race didn't just make individual organisms more sophisticated, it made the entire biosphere more complex and in many ways more dangerous. For the first time, evolution wasn't just about adapting to the physical environment, but about adapting to other life forms that were actively trying to kill you. We cannot know for certain what those first predators looked like, but fossil evidence from slightly later periods gives us hints. Some developed elaborate cellular machinery for paralyzing their prey. Others evolved the ability to inject digestive enzymes into their victims, liquefying them from the inside before consumption. Still others became masters of chemical warfare, producing toxins that could kill organisms much larger than themselves. The haunting question is, why did predation evolve at all? The honest answer is that it was probably inevitable once oxygen became abundant. Oxygen-powered metabolism was so efficient that it allowed organisms to grow larger and more complex. But larger organisms needed more food, and the most concentrated source of nutrients wasn't floating freely in the water, it was locked up inside other living things. By around 1.5 billion years ago, the fossil record shows evidence of what paleontologists call predator-prey dynamics preserved in stone. We see microscopic shells with precisely circular holes drilled through them, the calling cards of ancient hunters. We find cellular remains showing evidence of chemical warfare, with some organisms clearly having died from toxins produced by others. But the most haunting aspect of this development isn't the violence itself. It's the realization that predation created something that had never existed before on Earth: the concept of fear. For the first time, living organisms had to worry not just about finding food and reproducing, but about the constant possibility of violent death. This psychological dimension of early predation may seem like anthropomorphism, but recent research suggests that even single-celled organisms can exhibit behavior that looks remarkably like fear responses: rapid movement away from predators, chemical alarm signals, and even what appears to be stress-related cellular damage. And yet, as terrifying as these developments were, they were just the beginning. The evolution of predation set the stage for something even more dramatic: the rise of complex, multicellular life forms that would make the microscopic hunters of the Proterozoic look like toys. So the question remains, if single-celled predators could create such evolutionary chaos, what happened when cells learned to work together to create the first multicellular hunters? But before we can answer that question, we need to understand just how revolutionary the emergence of predation was for the fundamental organization of life on Earth. The transition from a cooperative to a predatory world wasn't just a change in behavior, it was a complete restructuring of biological reality that affected everything from cellular architecture to ecosystem dynamics. Recent advances in molecular paleontology have allowed scientists to study the preserved biochemical signatures of these ancient predator-prey interactions with unprecedented detail. What they've discovered is that the evolution of predation triggered cascading changes in cellular biology that were far more profound than anyone had previously imagined. The first and most immediate change was in cellular defense systems. Within perhaps a few million years of the first predators appearing in the fossil record, we see evidence of prey organisms developing sophisticated cellular armor. These weren't just thicker cell walls, they were complex, multi-layered defensive structures that represented some of the most advanced biological engineering in Earth's history at that time. Recent analysis of ancient cellular fossils has revealed defense systems of remarkable sophistication. Some organisms developed what we might call biological chainmail, interlocking protein structures that could flex and bend without breaking, providing protection against physical attack while maintaining cellular function. Others evolved chemical moats, concentrated toxins in their outer cellular layers that would poison any predator that attempted to breach their defenses. But perhaps most remarkably, some prey organisms developed what appears to be early warning systems, primitive sensory networks that could detect the approach of predators and trigger rapid defensive responses. These systems required levels of cellular organization and information processing that had never existed before in Earth's history. The predators, in turn, were forced to become increasingly sophisticated in their hunting strategies. Recent research has revealed that early cellular predators weren't just opportunistic scavengers. They were strategic hunters capable of remarkable behavioral complexity. Some developed what paleontologists call persistence hunting strategies, following individual prey organisms for extended periods until their targets exhausted their energy reserves and became vulnerable to attack. This required not just the ability to track prey over time, but also the capacity to assess the energy states of potential victims and make strategic decisions about when to attack. Others evolved pack hunting behaviors at the cellular level, coordinating their attacks with other predators to overwhelm prey that would have been too well defended for individual hunters to handle. Recent analysis of microfossil assemblages has revealed formations that appear to preserve ancient hunting grounds, where multiple predators work together to capture and process large numbers of prey organisms. The fossil evidence for these coordinated attacks is subtle, but unmistakable. We find prey remains that show evidence of damage from multiple predators, arranged in patterns that suggest systematic processing rather than random scavenging. Some formations preserve what appear to be the remains of cellular slaughterhouses, areas where coordinated groups of predators processed large numbers of victims in organized, efficient ways. But the most significant development was the evolution of what we might call predatory intelligence. The ability of hunting organisms to learn from experience, modify their behavior based on prey responses, and develop increasingly sophisticated strategies for capturing specific types of victims. Recent studies of trace fossils from this period have revealed evidence of predatory learning that is remarkable for its sophistication. Some ancient hunting grounds show clear patterns of tactical evolution, evidence that predator strategies became more refined and effective over time in response to evolving prey defenses. These weren't just random improvements due to natural selection, they appear to be examples of behavioral learning within individual predator lifetimes. Some fossilized hunting traces show evidence of strategy modification, that occurred too rapidly to be explained by genetic evolution alone. The implications of predatory learning extend far beyond hunting effectiveness. The capacity to learn, remember, and modify behavior based on experience represents one of the first examples of what we might call primitive intelligence in Earth's history. These early predators were demonstrating cognitive capabilities that wouldn't be matched by other organisms for hundreds of millions of years. Recent research has also revealed that the evolution of predation triggered the development of the first biological communication system specifically designed for survival rather than reproduction. Prey organisms began evolving chemical signaling networks that could warn other individuals of approaching threats, coordinate group defensive behaviors, and even share information about predator hunting strategies. These early warning systems were remarkably sophisticated for their time. Some organisms developed the ability to produce specific chemical signals that could convey detailed information about the type, size, and behavior of approaching predators. Others evolved the capacity to relay warning signals across considerable distances, creating communication networks that spanned entire microbial communities. The predators responded by developing counterintelligence capabilities, the ability to detect and interpret prey warning systems, and in some cases to produce false signals that could confuse or misdirect their intended victims. This led to an escalating information warfare between predators and prey that represented one of the first examples of biological deception in Earth's history. Recent molecular analysis has revealed that some ancient predators were capable of chemical mimicry, producing signals that made them appear to be harmless organisms or even potential mates to their prey. This level of deceptive capability required sophisticated biochemical systems and behavioral flexibility that was unprecedented in the history of life. But perhaps the most profound impact of early predation was its effect on the evolution of cellular complexity itself. The energy demands of predatory behavior, the need for rapid movement, sophisticated sensory systems, and complex behavioral coordination, created selective pressures for more efficient cellular organization. Recent research has revealed that many of the fundamental features of complex cells, specialized organelles, internal membrane systems, and sophisticated molecular machinery evolved in direct response to the challenges created by predator-prey dynamics. The mitochondria that power modern cells, for example, appear to have evolved from bacteria that were originally either predators or prey in ancient cellular ecosystems. The complex internal structure of modern cells reflects billions of years of evolutionary arms races between cellular predators and their victims. The evolution of the cell nucleus, the control center that houses genetic material in complex cells, may have been driven by the need to protect crucial genetic information from the chemical weapons and physical attacks of cellular predators. Recent research suggests that nuclear organization evolved as a defensive adaptation that allowed cells to sequester their most important biological information away from external threats. Even more remarkably, recent studies have revealed that some forms of cellular cooperation, the foundation of all multicellular life, may have originally evolved as anti-predator strategies. Some ancient organisms appear to have developed the ability to form temporary multicellular aggregations, specifically to resist predation by single-celled hunters. These early cooperative behaviors required unprecedented levels of cellular communication and coordination. Individual cells had to be able to recognize members of their own species, coordinate their movements and behaviors, and maintain group cohesion in the face of predatory attacks. Recent analysis of ancient microbial mats has revealed evidence of these early cooperative behaviors preserved in stone. Some formations show clear patterns of cellular organization that could only have resulted from active coordination between individual organisms, the first examples of true social behavior in Earth's history. The sophistication of these early social systems is remarkable. Some ancient microbial communities appear to have developed division of labor, with different cells specializing in different functions, some focused on sensing and responding to threats, others on nutrient gathering, still others on reproduction and growth. Recent isotope analysis has revealed that some of these early cooperative communities were capable of resource sharing on scales that approached those of modern social organisms. Individual cells that specialized in particular functions could share the products of their activities with other community members, creating the first biological economies based on specialization and exchange. But the most haunting aspect of this early predator-prey arms race was its relentless escalation. Each new defensive innovation by prey organisms created selective pressure for more sophisticated hunting strategies by predators. Each new predatory capability drove the evolution of more advanced defensive systems. This evolutionary feedback loop created conditions for rapid biological innovation that were unlike anything that had existed during the billions of years of purely cooperative life. The rate of evolutionary change accelerated dramatically as predators and prey pushed each other toward increasingly complex and sophisticated forms of organization. Recent studies of evolutionary rates during this period have revealed that biological innovation was occurring orders of magnitude faster than during the previous era of cooperative life. The diversity of cellular forms, the sophistication of biochemical systems, and the complexity of behavioral strategies all increased exponentially in response to predatory pressures. The fossil record from this period shows evidence of what paleontologists call evolutionary experimentation, rapid diversification of cellular forms and functions as organisms explored new strategies for survival in the predatory world. Some of these experiments were dead ends, representing evolutionary strategies that proved unsuccessful, but others laid the groundwork for innovations that would eventually lead to complex multicellular life. Recent analysis of ancient DNA sequences preserved in mineral formations has revealed that the genetic diversity of microbial communities increased dramatically during this period. The number of different species, the variety of metabolic strategies, and the complexity of ecological relationships all exploded in response to predatory pressures. And yet, even as these single-celled predators were transforming life on Earth through their hunting activities, they were also creating the conditions for their own obsolescence. The evolutionary pressures they created, the need for larger size, more sophisticated organization, and greater behavioral complexity, would eventually lead to the emergence of multicellular predators that would make their single-celled predecessors look primitive by comparison. The cellular cooperation that had evolved as a defense against single-celled predators would eventually be turned into a weapon, creating the first multicellular hunters with capabilities that no single cell could ever achieve. The microscopic predators of the Proterozoic had sown the seeds of their own replacement by creating the evolutionary conditions that would give rise to true multicellular monsters. These cellular giants would combine the individual capabilities of thousands or millions of cells into organized hunting machines that could track prey across vast distances, coordinate complex attacks, and process victims with efficiency that no single-celled predator could match. The age of cellular predation was about to give way to something far more terrifying, the age of multicellular monsters. Chapter 4: The Microscopic Monsters. The age of the unicellular giants. Around 1.2 billion years ago, something emerged in Earth's ancient oceans that challenges our understanding of what single-celled life can accomplish. These weren't the microscopic dots we typically associate with bacteria or simple protists. These were giants, single cells the size of grapes, some even larger, with internal structures so complex they resembled miniature cities, complete with specialized districts, transportation networks, and sophisticated machinery for capturing and processing food. It is strange to imagine, but before multicellular life became dominant, evolution experimented with making individual cells as large and sophisticated as possible. The result was a world populated by what we might call cellular monsters, organisms so bizarre and alien that they seem designed by a science fiction writer with a particularly dark imagination and an unlimited special effects budget. These giant cells weren't just scaled-up versions of familiar microorganisms, they were fundamentally different entities that pushed the boundaries of what single-celled life could achieve. To understand just how extraordinary they were, we need to appreciate the constraints that typically limit cell size in the modern world. Most cells are microscopic because of basic physics and chemistry. As cells grow larger, their volume increases much faster than their surface area. This creates problems with nutrient exchange, waste removal, and internal communication. A typical bacterial cell is only a few micrometers across because that's roughly the maximum size that allows efficient molecular transport across the cell membrane. But the giant cells of the Proterozoic era had found ways around these limitations. They developed complex internal membrane systems that increased their effective surface area. They evolved specialized organelles for different functions. Some even developed primitive circulatory systems that could transport materials across their enormous interiors. The evidence for these giant cells comes from fossil formations around the world, but some of the most spectacular examples are found in China's Dushantuo Formation, the Bitter Springs Formation in Australia, and similar deposits in Siberia and Scandinavia. Here, preserved in exquisite detail by rapid mineralization, are cells up to 200 micrometers across, visible to the naked eye and packed with internal structures that rival the complexity of modern animal cells. Recent advances in microscopy and chemical analysis have revealed that these fossils preserve not just cell outlines, but actual internal structures. We can see what appear to be nuclei, specialized organelles, internal membrane systems, and even what might be primitive cytoskeletons, protein networks that gave these giant cells their shape and structure. But here's the twist that makes these ancient giants truly terrifying. These weren't just large cells, they were cellular predators of unprecedented sophistication. Some species developed elaborate feeding structures that could extend outside the cell membrane like microscopic tentacles, capturing prey and drawing it inside for digestion. These feeding apparatus were marvels of cellular engineering, with jointed sections, muscular contractions, and even primitive sensory structures. Others evolved the ability to literally change shape, flowing like liquid to engulf their victims in a process that was part predation, part absorption, and part nightmare. Imagine a blob of living protoplasm the size of a grape that could flatten itself into a thin sheet to slide under potential prey, then surround and engulf organisms much larger than itself. The most haunting examples are the cells that developed internal storage chambers, specialized organelles where they could keep their prey alive for extended periods. These were essentially microscopic dungeons where captured organisms would be slowly digested over days or weeks, their nutrients extracted bit by bit while they remained alive and presumably aware of their fate. Fossil evidence suggests that some of these storage chambers could hold dozens of prey organisms simultaneously. The predator could essentially maintain a living pantry, consuming stored prey as needed while continuing to hunt for fresh victims. This level of food management was unprecedented in the history of life, and wouldn't be matched again until the evolution of complex animal behaviors millions of years later. We cannot know for certain how these cellular giants hunted, but the fossil evidence suggests they were capable of both active predation and what paleontologists call sit-and-wait strategies. Some appear to have anchored themselves to the ocean floor and waited for smaller organisms to drift within reach of their feeding apparatus. Others show evidence of mobility, the ability to actively swim through the water column in search of prey. Recent isotope analysis has revealed that some giant cells were capable of coordinated group behavior. Fossil assemblages show evidence of multiple giant cells working together to surround and capture prey that would have been too large or too fast for individual predators to handle. This suggests a level of communication and cooperation that was remarkable for single-celled organisms. The reveal is that these cellular monsters weren't just larger versions of simpler organisms, they were fundamentally different in their relationship to their environment. While smaller cells were largely at the mercy of ocean currents and chemical gradients, these giants could actively control their surroundings. They could choose where to go, what to eat, and when to reproduce. This level of environmental control was revolutionary. For the first time in Earth's history, individual organisms could modify their local environment to suit their needs. Some giant cells appear to have cultivated bacterial colonies as food sources, essentially becoming the first farmers. Others created chemical barriers around their territories that excluded competitors while attracting prey. Recent research has shown that some of these ancient cells developed what appears to be primitive nervous systems, networks of protein fibers that could transmit signals across the cell's interior faster than simple molecular diffusion would allow. This meant they could coordinate complex behaviors in ways that smaller organisms simply couldn't manage. These proto-nervous systems allowed giant cells to process multiple sensory inputs simultaneously and coordinate sophisticated responses. They could track multiple prey organisms at once, respond to threats while continuing to hunt, and even engage in what appears to be primitive learning behavior. But perhaps the most terrifying aspect of these cellular giants wasn't their size or their hunting abilities, it was their longevity. While smaller organisms might live for hours or days, some of these giants appear to have lived for months or even years. This gave them time to learn, to remember, and to develop increasingly sophisticated hunting strategies based on experience. Fossil trackways preserve evidence of individual giant cells that appear to have followed the same hunting routes repeatedly, suggesting they could remember productive areas and return to them regularly. Some formations show evidence of what looks like territorial behaviour, with certain areas apparently controlled by individual giant cells that excluded competitors and maintained exclusive hunting rights. The fossil record preserves evidence of what looks like cellular warfare on an unprecedented scale. Some formations show mass die-offs where thousands of smaller organisms appear to have been killed simultaneously, possibly by toxins released by competing cellular giants. These ancient battlefields stretch across entire fossil beds, suggesting conflicts that involved multiple giant cells and affected entire ecosystems. Others show evidence of what paleontologists call cellular cannibalism, larger cells that specialized in hunting and consuming other large cells. These super predators developed specialized apparatus for penetrating the defenses of other giant cells, essentially becoming the apex predators of their microscopic world. The chemistry of these ancient conflicts has been preserved in mineral replacements of organic tissues, revealing sophisticated biochemical weapons that were deployed in cellular warfare. Some giant cells produced toxins that could dissolve the cell membranes of their victims. Others developed chemical signals that could paralyze prey or interfere with their nervous systems. The honest answer is that we're still discovering the full extent of what these organisms were capable of. Recent fossil discoveries have revealed cells with internal structures so complex that they seem to blur the line between single-celled and multicellular life. Some appear to have been partitioned into dozens of specialized compartments, each with its own function in the cell's survival and reproduction. These compartments weren't just simple storage areas, they were sophisticated processing centers with their own specialized chemistry and function. Some were devoted to prey capture and processing, others to waste management and detoxification, still others to reproduction and cellular maintenance. Recent analysis has revealed that some giant cells had developed what appears to be primitive immune systems, cellular defenses that could recognize and destroy foreign organisms that had penetrated their defenses. This suggests a level of cellular complexity that approaches that of modern complex organisms, and yet, for all their sophistication and success, these cellular giants were doomed. The very traits that made them so effective, their size, their complexity, their energy demands, would become liabilities as Earth's environment continued to change and new forms of organization emerged. The haunting question that lingers is, if these single-celled monsters were so successful, so sophisticated, and so well adapted to their environment, what could possibly have been powerful enough to drive them to near extinction? The answer would emerge from an unexpected direction, not from environmental catastrophe or asteroid impacts, but from a revolutionary new form of organization that would change the rules of life itself. Cells were about to learn to work together, and when they did, the age of cellular giants would come to an end. Chapter 5: The Multicellular Revolution. When cells learn to conspire. There is a moment, approximately 800 million years ago, that represents one of the most profound betrayals in the history of life on Earth. Individual cells, which had spent billions of years perfecting the art of independence, developing increasingly sophisticated ways to survive and thrive on their own, began to give up their autonomy and work together in ways that would fundamentally transform the nature of existence itself. This wasn't cooperation in the way we typically understand it. This wasn't like modern social behaviors where individuals work together while maintaining their separate identities. This was something far more radical. Cells literally merging their identities, sacrificing their individual survival for the success of a larger collective, becoming so interdependent that they could no longer exist apart from one another. It was the birth of true multicellular life, and it would prove more devastating to the existing order than any extinction event that had come before. The cellular giants that had ruled Earth's oceans for hundreds of millions of years were about to face competition from organisms that operated on entirely different principles. Organisms that could achieve capabilities no single cell, no matter how sophisticated, could ever match. To understand the magnitude of this transition, we need to appreciate what individual cells were giving up when they chose cooperation over independence. For billions of years, cellular evolution had been driven by the imperative of individual survival. Every innovation, every adaptation, every evolutionary advance had been focused on making individual cells more capable, more efficient, more successful at surviving and reproducing. The giant cells we discussed in the previous chapter represented the pinnacle of this individual approach to life. They were marvels of cellular engineering, sophisticated, powerful, and supremely well adapted to their role as apex predators in ancient oceans. They had solved the fundamental problems of cellular existence through individual excellence. But individual excellence has limits. No matter how sophisticated a single cell becomes, it's still constrained by the basic physics and chemistry of cellular life. There are upper limits to how large a single cell can grow, how complex its internal organization can become, and how many different functions it can perform simultaneously. The evidence suggests that this transition to multicellular life happened multiple times in multiple lineages, but the most successful experiments occurred in what we now call the Ediacaran period, roughly 600 to 540 million years ago. Here, in fossil beds around the world, from the famous Ediacara Hills of Australia to the White Sea coast of Russia to the mountains of Namibia, we find the first evidence of organisms that were unmistakably more than the sum of their cellular parts. Recent analysis of these ancient fossils has revealed details that were invisible to earlier generations of paleontologists. Using electron microscopy, chemical analysis, and three-dimensional reconstruction techniques, scientists have been able to peer inside these ancient organisms and see how their cells were organized and connected. What they've found is remarkable. These early multicellular organisms weren't just loose aggregations of cells that happened to stick together. They were highly organized structures with clear patterns of cellular specialization, sophisticated communication systems between cells, and coordinated behaviors that no single cell could achieve alone. But here's the twist that makes this transition even more revolutionary than it first appears. These early multicellular organisms weren't just larger versions of single-celled life. They were fundamentally different in ways that made them terrifying competitors to everything that had come before. Individual cells, no matter how sophisticated, were limited by the physical constraints of being single units. They could only grow so large before their surface area became inadequate to exchange nutrients and waste with their environment. They could only become so complex before their internal organization became chaotic and their coordination systems became overwhelmed. Multicellular organisms shattered these limitations through a principle that would become one of the most powerful forces in evolutionary history: the division of labor. By specializing different cells for different functions, some for feeding, some for movement, some for reproduction, some for defense, some for sensory processing, they could achieve levels of efficiency and capability that no single cell could match. Think about it in terms of engineering principles. A single cell is like a Swiss Army knife, versatile and self-contained, but limited in what it can accomplish because it has to perform all functions with the same basic toolkit. A multicellular organism is like a factory, with specialized tools and workers for each task, capable of achieving levels of productivity and sophistication that no individual worker could match. The reveal is that this cellular cooperation created the first true predators capable of hunting organisms much larger than themselves. Where cellular giants had been limited to engulfing prey that could fit inside their membranes, multicellular predators could dismember their victims, break them down externally and consume them piece by piece. This wasn't just a quantitative change, bigger predators eating bigger prey. This was a qualitative revolution that introduced entirely new categories of predatory behavior. For the first time, predators could be smaller than their prey and still successfully hunt them. Size relationships were no longer the primary determinant of predatory success. Recent fossil evidence from Ediacaran formations has revealed some of the earliest examples of this new kind of predation. We find large, complex organisms with clear evidence of external damage that could only have been caused by smaller predators working together to overwhelm and dismember them. These are some of the first preserved examples of coordinated group predation in Earth's history. We cannot know for certain what these early multicellular predators looked like, but the fossil evidence suggests they were unlike anything in the modern world. Some appear to have been flat carpet-like organisms that could smother their prey like living blankets, surrounding and suffocating organisms much larger than their individual cells. Others developed the first true mouths, specialized openings lined with cells dedicated exclusively to processing food. These weren't just holes through which food could pass, but sophisticated feeding structures with specialized cell types for grasping, cutting, crushing, and chemically breaking down prey. Recent analysis has revealed that some early multicellular organisms developed primitive digestive systems. internal spaces where prey could be broken down by specialized enzymes produced by dedicated cell types. This allowed them to consume and process prey much more efficiently than single-celled predators, which had to accomplish all aspects of feeding with the same basic cellular machinery. The haunting question is, what was it like to be a single-celled organism in a world where multicellular predators were beginning to emerge? The honest answer is probably terrifying beyond our ability to imagine. For hundreds of millions of years, the largest threats in Earth's oceans had come from organisms roughly the same size as yourself, or at most, a few times larger. Competition was fierce, but it was competition between entities operating under the same basic constraints and limitations. Predation, when it occurred, followed predictable patterns based on size relationships and individual capabilities. Suddenly, single cells found themselves facing enemies that operated under completely different rules. These multicellular predators could be simultaneously smaller and larger than their individual cells, more coordinated than any single organism could be, and capable of hunting strategies that no individual cell could conceive or execute. The fossil record from this period shows evidence of what paleontologists call predatory innovation. Rapid evolutionary changes in both predator and prey species as multicellular hunters developed new weapons and their targets developed new defenses. This was an arms race unlike any that had occurred during the billions of years of single-celled dominance. Some single-celled organisms responded to the multicellular threat by developing thicker, more resilient cell walls that could resist physical damage from coordinated attacks. Others began producing more potent toxins, chemicals that could poison entire multicellular organisms rather than just individual attacking cells. Still others developed the ability to form defensive colonies, temporary multicellular structures that could resist predation more effectively than individual cells. These weren't true multicellular organisms in the modern sense, but they were steps in that direction, responses to predatory pressure that pushed single-celled organisms toward greater cooperation and coordination. But these were ultimately losing strategies. The advantages of true multicellularity, specialization, coordination, scalability, and efficiency, were simply too overwhelming. Within a relatively short period of geological time, measured in tens of millions of years rather than hundreds of millions, complex multicellular organisms had taken over the role of dominant predators in Earth's oceans. Recent research has revealed that this transition wasn't gradual or smooth. Fossil evidence suggests periods of rapid evolutionary experimentation, followed by mass extinctions as successful, multicellular forms displaced earlier organisms. Some formations preserve what appear to be ecological collapse events where entire communities of single-celled organisms were replaced by multicellular successors within short geological periods. And yet, the most terrifying aspect of this transition wasn't the rise of multicellular predators, it was what came next. Because once cells learned to cooperate in basic ways, they began experimenting with increasingly sophisticated forms of organization. They developed internal communication systems that allowed rapid coordination across large distances. They evolved specialized sensory cells that could detect threats and opportunities. They began to develop the first true nervous systems. For the first time in Earth's history, predators could think, plan, and coordinate their attacks in ways that went far beyond simple cellular responses to chemical gradients or physical stimuli. The age of intelligent hunting was about to begin, and it would make everything that had come before seem primitive by comparison. So the question remains, if multicellular cooperation was powerful enough to overturn billions of years of single-celled dominance, what happened when these collaborative organisms began developing true intelligence, the ability to process information, store memories, and make complex decisions about their environment and their behavior? The answer would emerge in the fossil record of the late Precambrian and early Cambrian periods, where we find evidence of organisms with nervous systems, sensory organs, and behaviors that suggest levels of cognitive sophistication that would have been impossible for any individual cell to achieve. Chapter 6: The First Brains. The birth of intelligent terror. Around 550 million years ago, something unprecedented emerged in Earth's oceans that would forever change the nature of predation, the dynamics of ecosystems, and ultimately the trajectory of evolution itself. The first nervous systems. For the first time in the planet's 4 billion-year history, hunters could think about their prey, plan their attacks, and learn from their experiences. It is strange to imagine, But before this moment, all predation had been essentially reflexive. Organisms responded to chemical signals, followed gradients of nutrients or other attractants, or simply bumped into their food by chance. Even the sophisticated cellular giants and early multicellular predators we've discussed operated primarily through programmed responses to environmental stimuli. There was no planning, no strategy, no anticipation of prey behavior, and no ability to modify hunting techniques based on past experience. The development of even primitive nervous systems changed everything. Suddenly, predators could process information from their environment, integrate data from multiple sensory sources, remember previous hunting experiences, and make decisions about where to go and what to attack. The age of mindless consumption was over. The era of intelligent predation had begun. To understand the magnitude of this development, we need to appreciate what nervous systems actually do and why they represent such a revolutionary innovation in biological organization. At their most basic level, nervous systems are information processing networks, biological computers that can receive sensory input, process that information, store memories, and coordinate appropriate responses. But nervous systems are more than just biological computers. They create something that hadn't existed before in Earth's history: the ability to model the environment internally and predict future events based on past experience. This gave organisms with nervous systems an enormous advantage over those without them, because they could anticipate rather than merely react. The evidence for these early nervous systems comes from exceptionally preserved fossils, particularly in famous formations like the Burgess Shale in Canada, the Chengjiang Biota in China, and similar deposits around the world that preserve soft tissues in extraordinary detail. Here we find organisms with clear neural structures, networks of specialized cells dedicated to processing information and coordinating behavior. Recent advances in fossil preparation and analysis have revealed details of these ancient nervous systems that were invisible to earlier generations of paleontologists. Using techniques like electron microscopy, chemical mapping, and three-dimensional reconstruction, scientists can now peer inside 550-million-year-old fossils and see individual nerve cells, brain structures, and sensory organs. What they've found is remarkable. These weren't the simple distributed nerve nets we see in modern jellyfish or other primitive organisms. Some of these ancient creatures had developed centralized nervous systems, primitive brains that could integrate information from multiple sensory inputs and coordinate complex multi-step behaviors. But here's the twist that makes these early brains even more significant. They weren't just processing sensory information about the immediate environment. Evidence suggests they were capable of what we might call predictive modeling, the ability to anticipate future events based on current information and past experience. This created a fundamental shift in the predator-prey dynamic. For the first time, prey organisms faced predators that could think ahead, plan attacks, and modify their behavior based on the prey's responses. It was no longer enough to have good defenses against reflexive predators. Prey organisms now needed defenses against intelligence. One of the most haunting examples from this period is Opabinia, a bizarre predator roughly the size of your hand that lived around 505 million years ago. It had 5 mushroom-shaped eyes on stalks that could move independently, giving it nearly 360-degree vision and the ability to track multiple objects simultaneously. Its most distinctive feature was a long, flexible proboscis, tipped with a claw-like structure that it used to snatch prey from the seafloor. Recent analysis of Opabinia fossils has revealed that its brain was proportionally larger and more complex than those of many modern arthropods. The structure of its neural pathways suggests it could coordinate the movement of its eyes with its feeding appendage, tracking potential prey while positioning itself for the most effective attack. But what made Opabinia truly terrifying wasn't its bizarre anatomy, it was its behavior. Fossil evidence suggests it could coordinate complex hunting sequences that required integrating information from multiple sensory sources, planning multi-step approaches to prey capture, and adjusting its strategy based on prey responses. This required a level of neural integration that was revolutionary for its time. The reveal is that these early brains didn't just make predators more effective, they made them unpredictable. Prey organisms had evolved defenses against reflexive predators, creatures that followed predictable response patterns to environmental stimuli. But how do you defend against an enemy that can think, plan, and adapt its strategy based on your behavior? This question drove one of the most dramatic evolutionary radiations in Earth's history. Faced with intelligent predators, prey organisms were forced to develop new categories of defense that went far beyond simple physical or chemical protection. They needed to become unpredictable themselves, developing complex escape behaviors, sophisticated sensory systems for early threat detection, and even primitive forms of deception and camouflage. We cannot know for certain what it was like to be hunted by these early intelligent predators, but the fossil record suggests it was a traumatic transition for most marine ecosystems. The diversity of defensive strategies that evolved during this period is staggering. Elaborate armor systems, sophisticated chemical defenses, complex escape behaviors, advanced camouflage techniques, and even the first evidence of coordinated group defense strategies. Recent analysis of trace fossils from this period has revealed evidence of increasingly complex predator-prey interactions. We see trackways that suggest predators following prey trails for extended distances, evidence of ambush behavior at specific locations, and even what appear to be collaborative hunting strategies involving multiple predators working together. Some prey species developed what paleontologists call predator confusion strategies, bizarre asymmetrical body plans that made it difficult for predators to determine which end was the head and which was the tail, where the mouth was located, or which direction the organism was likely to move. These evolutionary grotesques were the first examples of biological deception, designed to confuse intelligent predators. Others evolved rapid escape responses, developing the first true muscles capable of explosive movement. These weren't the slow, hydraulic movement systems of earlier organisms, but fast-twitch muscle fibers that could generate enormous accelerations in milliseconds, allowing prey to escape from predators that might be faster in sustained movement but slower to react. Still others developed sophisticated chemical defense systems that went beyond simple toxicity. Some organisms evolved the ability to release chemical signals that could confuse predator sensory systems, essentially creating biological smokescreens that made tracking and capture more difficult. But perhaps the most significant development was the evolution of sensory awareness in prey species. For the first time, organisms began developing sophisticated eyes, chemical sensors, pressure-sensitive organs, and even primitive forms of electroreception that could detect approaching predators at considerable distances. This sensory arms race led to some of the most sophisticated detection systems in the animal kingdom. Some organisms developed compound eyes with thousands of individual lenses, each capable of detecting movement across a small portion of the visual field. Others evolved chemical sensors so sensitive they could detect individual molecules of predator-produced chemicals in seawater. The honest answer is that this neural arms race created an explosion of biological innovation, unlike anything Earth had seen before. The Cambrian period, which began around 541 million years ago, saw the rapid evolution of almost every major body plan that exists today. And at the heart of this diversification was the constant pressure of intelligent predation. Recent phylogenetic analysis has revealed that nervous system complexity increased dramatically during this period, not just in predators, but in prey species as well. The fossil record shows evidence of increasingly sophisticated brains, more complex sensory organs, and more coordinated behaviors in organisms across multiple lineages. But the development of nervous systems also led to something even more revolutionary: the first evidence of learning and memory in individual organisms. Trace fossils preserve evidence of individual animals that appear to have modified their behavior based on experience, returning to successful hunting or feeding areas and avoiding locations where they had encountered threats. The haunting question that lingers is this: if the development of simple brains could trigger such an explosion of evolutionary innovation, what happened when these neural systems became even more sophisticated? When organisms developed not just the ability to think and plan, but to communicate their thoughts and coordinate their behaviors with others of their kind? The answer emerges in the fossil record of the mid-Cambrian, where we find evidence of predators with neural capabilities that approach those of modern arthropods. These weren't just thinking hunters, they were problem-solving hunters, capable of learning from experience, adapting their strategies over time, and even teaching successful techniques to others. And yet, even these sophisticated neural predators pale in comparison to what would emerge next. The first organisms capable of coordinated group hunting, social learning, and collective intelligence that could accomplish things no individual brain, no matter how sophisticated, could achieve alone. So the question remains, if individual intelligent predators could reshape entire ecosystems, driving the evolution of new body plans, new behaviors, and new ecological relationships, what happened when they learned to work together, to share information, and to coordinate their hunting strategies across groups of individuals? Chapter 7, The Great Hunts. The first swarms of predators. There is a moment in the fossil record, roughly 480 million years ago, that preserves one of the most chilling scenes in prehistoric life, evidence of the first coordinated group hunt. In limestone formations in Morocco, paleontologists have found the remains of dozens of primitive arthropods arranged in what can only be described as a hunting formation, a prehistoric killing ground that captures the instant when individual intelligence evolved into collective intelligence, when thinking predators learned to think together. These weren't random aggregations of individual predators that happened to die in the same location. The positioning was too precise, the size distribution too systematic, and the prey remains scattered throughout the formation too clearly organized to be coincidental. The evidence points to a single, inescapable conclusion. These ancient organisms had learned to hunt in packs, coordinating their individual intelligence into something far more dangerous than the sum of its parts. It is strange to imagine, but long before wolves learned to coordinate their attacks on large herbivores, before dolphins developed sophisticated hunting strategies that require precise timing and communication, before humans began working together to bring down megafauna, arthropods in Earth's ancient seas had already mastered the art of collective predation. To understand how revolutionary this development was, we need to appreciate what coordinated hunting actually requires. It's not just about multiple predators attacking the same prey. That can happen by coincidence or simple opportunism. True coordinated hunting requires communication systems, role specialization, strategic planning, and the ability to adjust tactics in real time based on prey behavior and environmental conditions. The evidence suggests that these early pack hunters were ancestors of modern arthropods, creatures with segmented bodies, jointed legs, and compound eyes that gave them sophisticated sensory capabilities. But their hunting behavior was far more sophisticated than anything we see in their modern descendants, with the possible exception of some highly social insects. The fossil formations from this period preserve evidence not just of successful hunts, but of the organizational structures that made them possible. We can see clear evidence of role specialization within hunting groups, with different types of individuals positioned to just Capítulo 3. Los primeros cazadores. El nacimiento de la depredación. There is a moment, roughly 1.8 billion years ago, when something unprecedented happened in Earth's oceans. For the first time in the planet's history, one living thing looked at another living thing and saw not a neighbor, not a competitor for resources, not even an obstacle to avoid, but a meal. This moment represents one of the most profound shifts in the history of life, the birth of predation. Before this moment, life had been surprisingly cooperative. For over 2 billion years, organisms had competed for resources, certainly, but they didn't actively hunt and kill each other for food. The earliest life forms were content to absorb nutrients from their environment, break down organic matter that they encountered, or harness energy from chemical reactions with the minerals around them. They were, in essence, the world's first vegetarians. Though in a world without plants, without photosynthesis as we know it, without any of the complex biochemistry that we associate with modern ecosystems. This early cooperative world wasn't peaceful in the way we might imagine peace. Competition for resources could be fierce. Organisms developed chemical weapons to poison competitors. They built protective structures to exclude others from prime territories, and they evolved strategies to consume resources more efficiently than their neighbors. But they didn't hunt. They didn't kill for food. They didn't look at other living organisms as potential meals. The fossil evidence for this transition is subtle, but unmistakable. In rock formations from around 1.8 billion years ago, we begin to find the first clear signs of what paleontologists call predator-prey interactions. These aren't dramatic fossilized chase scenes or obvious evidence of violence. Instead, they're tiny holes drilled through ancient microbial structures, chemical signatures that suggest cellular contents were extracted by external forces, and statistical patterns in fossil assemblages that indicate some organisms were systematically consuming others. The evidence suggests that the first predators were microscopic, single-celled organisms not much different in size from their prey. But their impact was anything but small. These weren't the dramatic hunters we might imagine. There were no chase scenes across ancient seafloors, no dramatic struggles between predator and prey. Instead, these early predators simply engulfed their prey whole, like cellular Pac-Man games playing out in ancient seas. But to understand why this development was so revolutionary, we need to think about what predation actually means in biological terms. Predation isn't just about one organism eating another. It's about actively seeking out, pursuing, capturing, and consuming living organisms specifically for their nutritional value. It requires sensory systems to detect prey, mobility systems to pursue them, capture mechanisms to subdue them, and digestive systems to process them. More importantly, predation requires a fundamental shift in how organisms relate to their environment. Instead of simply reacting to chemical gradients or physical conditions, predators must actively assess their surroundings, make decisions about which organisms to pursue, and coordinate complex behaviors to achieve successful captures. But here's the twist that makes this evolutionary development even more significant. The evolution of predation didn't just add a new character to life's story, it completely rewrote the rules. Suddenly, being alive wasn't just about finding food and reproducing, it was about not becoming food for something else. For the first time in Earth's history, organisms had to worry about being killed by other organisms, not just by environmental conditions. This triggered what scientists call an evolutionary arms race, and it was unlike anything that had happened in the previous 2 billion years of life's history. Prey organisms began developing defenses, thicker cell walls to resist being penetrated, toxic chemicals to make themselves unpalatable, better sensory systems to detect approaching predators, and faster movement to escape capture. Predators responded by developing better weapons, more efficient hunting strategies, stronger digestive systems that could break down defensive structures, improved sensory abilities to track prey more effectively, and more sophisticated capture mechanisms. Each innovation by prey organisms created selective pressure for counter-innovations by predators, and vice versa. The reveal is that this arms race didn't just make individual organisms more sophisticated, it made the entire biosphere more complex and in many ways more dangerous. For the first time, evolution wasn't just about adapting to the physical environment, temperature, chemistry, light levels, pressure. Now evolution was also about adapting to other life forms that were actively trying to kill you. This created what evolutionary biologists call coevolutionary dynamics, situations where the evolution of one species directly influences the evolution of another species, evolution of another, creating feedback loops that can drive rapid and dramatic evolutionary change. Predator-prey coevolution would become one of the most powerful engines of biological innovation in Earth's history. We cannot know for certain what those first predators looked like, but fossil evidence from slightly later periods gives us hints about what early predation might have involved. Some of the earliest clear predators appear to have been amoeba-like organisms that could change their shape to engulf prey. Others developed specialized feeding structures, primitive versions of the complex feeding apparatus we see in modern single-celled predators. Some developed elaborate cellular machinery for paralyzing their prey, using chemical compounds that could disable the nervous systems or metabolic processes of their victims. Others evolved the ability to inject digestive enzymes into their victims, essentially liquefying them from the inside before consumption, a feeding strategy that we still see in some modern spiders and other arthropods. Still others became masters of chemical warfare, producing toxins that could kill organisms much larger than themselves. These weren't just defensive chemicals designed to make the producer unpalatable, they were offensive weapons designed to actively harm other organisms for the purpose of making them easier to consume. Recent research has revealed that some early predators may have developed what we might call hunting strategies, coordinated behaviors designed to increase capture success. Evidence from fossilized microbial mats suggests that some predators learned to position themselves along the edges of these communities, where they could intercept organisms moving between different areas. Others appear to have developed sit-and-wait strategies, positioning themselves in areas where prey organisms were likely to pass and remaining motionless until an opportunity presented itself. Still others seem to have been active hunters, moving through their environment in search of prey rather than waiting for prey to come to them. The haunting question is, why did predation evolve at all? Why did some organisms make the transition from absorbing nutrients from their environment to actively hunting and killing other organisms for food? The honest answer is that it was probably inevitable once oxygen became abundant in Earth's atmosphere. Oxygen-powered metabolism was so much more efficient than anaerobic processes that it allowed organisms to grow larger and more complex than anything that had existed before. But larger, more complex organisms needed more food, and the most concentrated source of nutrients wasn't floating freely in the water. It was locked up inside other living things. Think about it from a purely energetic perspective. An organism that could capture and consume another organism would gain access not just to the nutrients that the prey had collected from its environment, but also to all the complex organic molecules that the prey had synthesized: proteins, lipids, carbohydrates, and nucleic acids. This was like gaining access to pre-processed concentrated nutrition rather than having to extract basic nutrients from the dilute solutions available in seawater. But predation offered more than just nutritional advantages. It also provided access to resources that were otherwise unavailable. Some organisms had developed the ability to synthesize rare or complex molecules that others couldn't produce. By consuming these organisms, predators could gain access to these molecules without having to evolve the complex biochemical machinery needed to synthesize them. Recent isotope analysis of ancient microbial communities has revealed something fascinating. The first predators weren't necessarily larger than their prey. Many appear to have been roughly the same size, or even smaller in some cases. This suggests that early predation was more about accessing specialized nutrients or biochemical capabilities than about simple size-based dominance. By around 1.5 billion years ago, the fossil record shows clear evidence of what paleontologists call predator-prey dynamics, preserved in stone. We see microscopic shells with precisely circular holes drilled through them, the calling cards of ancient hunters that had developed specialized boring apparatus to access the soft tissues inside protective structures. These holes aren't random damage or decay artifacts. They're perfectly circular, positioned in specific locations on the shells, and often occur in clusters that suggest systematic hunting behavior. The size and shape of these holes can tell us about the organisms that made them, and statistical analysis of their distribution patterns can reveal information about ancient predator behavior. We find cellular remains showing evidence of chemical warfare, with some organisms clearly having died from toxins produced by others. The chemistry of these ancient toxins, preserved in mineral replacements of organic tissues, tells us about sophisticated biochemical weapons that were being deployed in microscopic battlefields 1.5 billion years ago. But perhaps most haunting are the fossil assemblages that preserve what appear to be mass predation events. In some formations, we find layers containing thousands of small organisms that all appear to have died simultaneously, often with evidence of partial consumption or chemical attack. These may represent some of the earliest examples of coordinated predation, multiple predators working together to overwhelm large populations of prey. The psychological dimension of early predation may seem like anthropomorphism, but recent research suggests that even single-celled organisms can exhibit behavior that looks remarkably like fear responses. Modern experiments with predatory amoeba and their prey have shown that potential prey organisms can detect chemical signals from predators and respond with rapid movement away from the source, changes in cellular activity that resemble stress responses, and even alterations in reproductive behavior that suggest they're responding to increased mortality risk. If modern single-celled organisms can exhibit these kinds of responses, it's likely that similar dynamics existed in ancient microbial communities. For the first time in Earth's history, living organisms had to worry not just about finding food and reproducing, but about the constant possibility of violent death. This created entirely new categories of evolutionary pressure. Organisms had to balance the need to find food with the need to avoid becoming food. They had to develop sensory systems that could detect threats as well as opportunities. They had to evolve behaviors that would minimize their risk of predation, while maximizing their own survival and reproduction. The fossil record from this period shows an explosion of defensive innovations that would be impressive in any era of Earth's history. Some organisms developed thick mineralized shells that made them difficult to consume. Others evolved chemical defenses, toxins that would poison any predator that attempted to eat them. Still others developed behavioral defenses. the ability to detect approaching predators and take evasive action, the formation of protective aggregations that made individual capture more difficult, and even primitive forms of camouflage that made detection less likely. But predators weren't standing still in this arms race. They developed counter-adaptations to overcome each new defense that prey organisms evolved. Stronger boring apparatus to penetrate thicker shells, detoxification systems to neutralize chemical defenses, better sensory systems to detect camouflaged prey, and hunting strategies that could overcome protective aggregations. Recent analysis of ancient microbial communities has revealed that this predator-prey arms race led to some of the first examples of what we might call ecological specialization. Instead of being generalists that could consume a wide variety of resources, some organisms began to specialize in hunting specific types of prey. This specialization created more complex ecological relationships than had ever existed before. Predators became dependent on specific prey species, while prey species evolved defenses against specific predators. The result was the emergence of the first true food webs, complex networks of feeding relationships that connected multiple species in intricate patterns of dependence and competition. And yet, as terrifying as these developments were for the organisms living through them, they were just the beginning. The evolution of predation set the stage for something even more dramatic: the rise of complex multicellular life forms that would make the microscopic hunters of the Proterozoic look like toys. The single-celled predators we've been discussing were limited by their basic biology. They could only grow so large, process so much information, and coordinate such simple behaviors. But the evolutionary pressures created by predation would eventually drive the evolution of organisms that could overcome these limitations through a revolutionary strategy: cooperation between cells. So the question remains, if single-celled predators could create such evolutionary chaos, such rapid innovation, such fundamental changes in the nature of life itself, what happened when cells learned to work together to create the first multicellular hunters? The answer would transform not just predation, but the very definition of what it means to be alive. Chapter 8: The First Engineers of Terror. When predators learned to build traps, around 450 million years ago, something appeared in the fossil record that fundamentally challenges our understanding of prehistoric intelligence. Evidence of the first constructed hunting traps. These weren't mere burrows or temporary shelters, they were deliberate engineered structures designed with one purpose: to capture, confine, and kill. There comes a moment when you realize that the line between hunting and engineering is far thinner than we imagine. In the Ordovician seas, certain predators crossed that line, becoming not just hunters, but architects of death. For the first time in evolutionary history, killing could be outsourced to a design, a mechanism, a structure waiting silently beneath the waves. The proof comes not from bones, but from trace fossils, preserved impressions and formations in ancient sediments that bear unmistakable signs of planning. These traces are not the random scrawls of foraging or the accidental shapes of sediment collapse. They are organized, multi-chambered, structured with entrances and exits, with carefully shaped channels that guided water flow and with it, unsuspecting prey. Some even contain internal cavities that appear to have been used as storage chambers, small prisons where living victims were held until the predator was ready to feed. The most spectacular evidence lies in limestone beds across Estonia and Sweden. There, paleontologists have uncovered labyrinths beneath the fossilized seafloor. Networks of burrows interconnected in a way that rivals the complexity of modern ant colonies. These were not chaotic or haphazard. The tunnels and chambers are positioned with striking efficiency, designed to funnel prey into tight spaces where escape was nearly impossible. The layout suggests careful forethought, a kind of architectural instinct guided not just by immediate hunger, but by anticipation of what would happen next. And here's the revelation that unsettles even seasoned scientists. The builders of these death machines were not large-brained vertebrates or early cephalopods. They were arthropods, creatures whose nervous systems were scarcely larger than the head of a pin. Yet within those tiny neural circuits emerged something extraordinary: engineering. Behavior that looks less like simple instinct and more like strategy. This was more than a hunting tactic. It was a shift in the entire predator-prey dynamic. For the first time in Earth's history, predators no longer had to be present at the kill. They could let the environment itself do the work. They could construct a device, withdraw to safety, and return later to reap the rewards. It was the dawn of passive predation, killing without direct confrontation. We cannot know exactly how these builders learned to construct their traps, but the fossil evidence whispers a story of learning, imitation, and innovation. In different regions, we see distinct architectural dialects. Some trap systems are straight and linear, like corridors designed for speed. Others are coiled and circular, forcing prey to spiral inward to their doom. Still others form intricate networks with multiple layers, suggesting that successful designs were copied, modified, and transmitted. A primitive kind of cultural inheritance long before the first human carved a stone tool. Even more astonishing is the record of iterative improvement. Early constructions are relatively simple, a single tunnel with a widened chamber at the end. But later designs grow increasingly sophisticated, with false entrances to confuse intruders, narrow choke points to prevent escape, and even what appear to be testing chambers, spaces where prey could be immobilized, perhaps examined before being consumed. These refinements imply that the builders were not just instinctively digging, but evaluating results and making adjustments. That raises a haunting question. What does it mean for intelligence when an organism can imagine not only its own actions, but the future behavior of another creature? To build a trap, you must anticipate. You must predict how your prey will move, what will attract it, and how it will react when cornered. This requires a mental model of the other, a simulation of another mind, however primitive. Recent analysis of these fossilized trap systems has revealed even more disturbing details. Some structures show evidence of repeated modification. Tunnels are widened in one layer of sediment, narrowed again in the next, as though the builders were conducting experiments, adjusting dimensions, refining angles, adapting to the responses of their prey. This suggests a level of feedback-driven behavior, a loop of observation and correction that borders on the beginnings of abstract thought. These arthropods weren't simply reacting, they were designing, testing, and redesigning. And yet, perhaps the most terrifying dimension of this story is not the individual ingenuity of a single trap builder, but the collective impact of many. Certain fossil beds reveal entire landscapes transformed into engineered killing fields. Networks of traps stretch for hundreds of meters, saturating the seafloor with death zones. To a small Ordovician fish or worm, wandering into such an area would have been like stepping into a minefield, except the mines weren't explosive, they were alive. Even more startling is the evidence that in some places multiple species of trap builders work together. Hybrid structures exist where two different engineering approaches seem to fuse, creating designs that neither species could have produced alone. Whether this was cooperative construction, opportunistic modification, or some bizarre form of ecological symbiosis, we cannot say. But the result is undeniable. More effective killing machines, born from the combination of multiple predatory minds. The implications stretch far beyond paleontology. For decades, intelligence has been measured in terms of brain size, tool use, and problem-solving in vertebrates. But these ancient arthropods suggest something different, that intelligence is not a singular, linear scale, but a spectrum of strategies. They remind us that complex problem-solving can emerge in tiny brains if the evolutionary pressures are strong enough. Intelligence may not be rare at all. It may simply take unfamiliar forms, and yet, despite their ingenuity, these marine engineers were still bound by the physics of their environment. Water currents, sediment stability, and the limited palette of marine construction materials defined what they could achieve. For all their sophistication, their traps were carved from mud and sand, vulnerable to collapse or erosion. The true revolution in predatory engineering was still to come, because when life began to invade the land, everything changed. The toolkit of a predator expanded dramatically. Soil, stone, plants, and even gravity itself became materials and forces that could be harnessed. On land, a trap could be built not just to confine, but to conceal. Pits could be dug, camouflaged with leaves, rocks could be balanced and toppled. Entire microenvironments could be reshaped to lure, capture, or kill. So the question echoes forward through time. If the shallow seas of the Ordovician produced hunters capable of architecture, what happened when their descendants crawled onto land? When they encountered a world where the rules of physics, chemistry, and biology opened entirely new frontiers of construction, what forms of terror did evolution design then? The story of the first engineers of terror is not simply about prehistoric creatures digging holes. It is about the dawn of foresight, the moment life began to shape its environment not just to survive, but to dominate. These ancient arthropods, with brains no larger than grains of sand, were already playing a game we often think belongs only to us, the game of invention. And in their silent, patient traps, we see the earliest blueprint of a truth that stretches across the eons. Intelligence, in whatever form it takes, is a weapon. Chapter 9: The Terrestrial Invasion. When horror reached the land around 400 million years ago, something emerged from Earth's ancient seas that would forever alter the destiny of life on land: the first terrestrial predators. And contrary to what we might imagine, these pioneers were not clumsy, gasping creatures fumbling their way into a strange new world. They were already masters of the hunt, veterans of aquatic battlefields who carried with them millions of years of evolutionary refinement. When they set claw upon solid ground, they did so not as wanderers, but as conquerors. It is one of the most unsettling truths in natural history. The conquest of land was not led by gentle herbivores nibbling on primitive plants, nor by timid scavengers creeping between mosses. It was led by hunters. To them, the terrestrial world was not a place to adapt to. It was a new arena, an untouched hunting ground brimming with fragile prey utterly unprepared for the violence that waited. The fossil record confirms this chilling story. In ancient beds of Scotland, Canada, and Australia lie the remains of arthropods that bear the unmistakable marks of terrestrial adaptation. Their jointed limbs were restructured for walking, their breathing systems modified to extract oxygen from air, and their sensory organs recalibrated to the physics of light, sound, and scent above water. These were not creatures swept onto land by accident. They were purpose-built predators who had crossed the boundary deliberately, carrying with them the evolutionary toolkit to dominate. Among them, none were more formidable than the Eurypterids, the so-called sea scorpions. Some species reached lengths of 2 meters, their armored bodies bristling with claws, stingers, and cutting appendages. Imagine a predator the size of a large dog, but armored like a tank and moving with the eerie precision of an insect. They were the terror of rivers, tidal flats, and early shorelines. And in time, their descendants would give rise to scorpions, spiders, and other land-based hunters that continue their legacy of stealth and venom today. What made land so revolutionary for predators was not simply the abundance of prey, it was the rules of physics themselves. In water, prey could escape in 3 dimensions: upward, downward, sideways. But on land, movement was largely restricted to 2 dimensions, flattening the battlefield in favor of the hunter. In water, vibrations and chemical cues diffuse quickly, becoming distorted by currents. On land, scent trails could linger for hours, and vibrations travelled cleanly through the ground. Sound carried farther, sharper. Vision reached greater distances. For the first time, predators could stalk with precision, track with persistence, and strike with speed unmatched in their aquatic origins. And strike they did. Within only a few million years of their arrival, the fossil record shows ecosystems reshaped around the predator-prey dynamic. Terrestrial life, which had barely begun to take root in the form of mosses, primitive ferns, and small invertebrates, was immediately forced into an evolutionary arms race. What did these early terrestrial worlds look like? Imagine alien gardens, carpets of moss, clusters of knee-high plants, and forests of stalks and fronds rising only a meter tall. There were no towering trees, no birdsong, no mammals bounding through undergrowth. The air was thick, heavy with humidity, and oxygen levels were higher than today, fueling arthropods to monstrous sizes. Now picture, within this alien terrain, predators the size of wolves creeping between the fronds. Their exoskeletons gleamed in the dim light. Their eyes, multifaceted and cold, scanned for movement. Their stingers dripped with venom that no terrestrial prey had yet evolved resistance against. For the first herbivores and detritus feeders to crawl ashore, it must have been nothing less than a nightmare. To be prey in this era was to live in a perpetual state of terror. Water had provided buoyancy, speed, and hiding places. On land, there was only gravity and the thin shelter of plants too small to conceal. Every sound, every vibration could mean death. Land offered predators hunting methods that were impossible in the sea. They learned to weaponize gravity, dropping onto prey from elevated rocks or plants. They used the firmness of the ground to pin victims with crushing strength. Unlike in shifting aquatic currents, they could claim permanent territories, memorizing every hollow, every shadow, every ambush point. Fossil trackways, ancient footprints pressed into Devonian mud, reveal something even more remarkable: endurance hunting. Some predators were capable of following prey across long distances, pacing them step by step. This is a style of pursuit later perfected by wolves, lions, and humans, but its roots go back to these first land arthropods. Imagine being chased not for seconds, but for hours, across barren ground, the sound of clawed footsteps never far behind. But perhaps most terrifying is that these predators did not abandon the engineering instincts of their aquatic ancestors. Just as earlier arthropods had built death traps in sediment beneath the seas, their terrestrial descendants modified landscapes for hunting. Burrows became more than shelters. They became snares, funnels, and execution chambers. Prey could stumble across terrain that was already weaponized, sculpted to end their lives. Some evidence suggests entire networks of burrows and tunnels built by predator colonies, creating killing grounds where any intruder would be funneled into danger. It is not difficult to imagine the terror of a small invertebrate scuttling across moss, only to find every escape route leading into the waiting claws of a hunter. Yet the true revolution was not in weapons, but in perception. On land, vision expanded. Shadows and light became tools. Some predators evolved enormous compound eyes with thousands of lenses, capable of detecting the faintest twitch of movement. Others honed chemical sensors to follow scent trails across kilometers. Still others became attuned to vibrations in the soil, able to sense footsteps long before prey came into sight. These adaptations created selective pressures that would forever shape terrestrial evolution. Prey began to develop camouflage, disguising themselves as leaves or bark. Others evolved warning colors, bright reds, yellows, and blacks announcing venom or foul taste. Still others grew wings, taking to the air to escape hunters tied to the ground. Flight, camouflage, mimicry, all of these hallmarks of terrestrial life were born in the crucible of predator-prey struggle. Unlike the shifting, ever-changing environment of the sea, land offered permanence. A predator could map its territory and learn it intimately, turning every rock, every crevice into an ally. Prey entering such territory stood little chance. The hunter knew every possible escape route before the chase even began. This created the first predator domains, areas where prey could enter but rarely leave alive. It was a kind of territorial ownership that prefigured the hunting ranges of wolves, tigers, and other apex predators millions of years later. The colonization of land by predators was not simply a biological milestone, it was a revolution. It forced prey to evolve defenses that would cascade through the history of life: shells, spikes, toxins, speed, intelligence. Every adaptation of prey was met by a counter-adaptation of predators, driving the endless arms race that defines ecosystems to this day. And yet these first hunters were only the beginning. As time passed, terrestrial predators grew larger, stronger, and more specialized. From armored arthropods came spiders, scorpions, and insects. From amphibious hunters came reptiles with bone-crushing jaws. And eventually, from small mammalian forms came predators capable not only of hunting, but of planning, coordinating, and imagining. The first footsteps of predators on land set the stage for everything that followed. For the rise of forests, for the birth of flight, for the appearance of intelligence itself. So the question remains, echoing across deep time: if the first terrestrial predators were already so devastating, what horrors emerged when evolution gave hunters not just size and strength, but strategy, cooperation, and cunning? The invasion had only begun. Chapter 10: The Giants of the Carboniferous. When the arthropods ruled the world around 350 million years ago, Earth's atmosphere underwent a transformation that created conditions perfect for the evolution of monsters. Oxygen levels rose to an unprecedented 35% of the atmosphere, nearly twice what we breathe today, and this oxygen-rich environment allowed arthropods to grow to sizes that seem impossible by modern standards, creating a world where giants walked, crawled, and flew across landscapes that resembled alien planets more than anything in our modern world. There is a moment in the Carboniferous period when you might have looked up through the steamy air of a primitive forest to see a dragonfly with a wingspan of 70 centimeters casting shadows like a small aircraft. The sound of its wings would have been audible from hundreds of meters away, not the gentle buzz of modern dragonflies, but a deep, rhythmic beating that announced the presence of an aerial predator capable of taking prey the size of small birds. You might have encountered millipedes 2 meters long crawling through the undergrowth like living trains, their hundreds of legs creating a sound like continuous rainfall as they move through the leaf litter. Or centipedes the size of alligators hunting through the forest floor with venomous claws capable of bringing down prey much larger than themselves, their sensory systems so sophisticated they could track victims through the complex three-dimensional maze of carboniferous forests. These weren't just scaled-up versions of modern arthropods. They were fundamentally different organisms, with physiologies adapted to high-oxygen environments and ecological roles that no longer exist on Earth. They were the apex predators of their time, ruling terrestrial ecosystems with a dominance that wouldn't be matched until the rise of dinosaurs, and surpassing even dinosaurs in some measures of ecological control. To understand how extraordinary these giants were, we need to appreciate the physiological constraints that normally limit arthropod size. Modern arthropods are restricted in size by their respiratory systems, which rely on passive diffusion of gases through a network of tubes called tracheae. This system works well for small organisms but becomes increasingly inefficient as body size increases, because the distance that oxygen must travel to reach internal tissues increases faster than the capacity of the respiratory system to deliver it. The high oxygen atmosphere of the Carboniferous period effectively eliminated this constraint. With nearly twice as much oxygen available in each breath, arthropod respiratory systems could support much larger body sizes. But the giants of this period didn't just grow larger, they evolved entirely new physiological systems to take advantage of the oxygen-rich environment. Recent analysis of Carboniferous arthropod fossils has revealed respiratory systems of unprecedented complexity. Instead of the simple tracheal networks of modern arthropods, these giants had elaborate branching systems with specialized structures for oxygen storage, active ventilation mechanisms, and even primitive circulatory systems that help transport oxygen to distant body parts. The evidence for these giants comes from exceptionally preserved fossil sites around the world, but some of the most spectacular examples are found in coal deposits, the compressed remains of Carboniferous forests that preserve these creatures in remarkable detail. The Mazon Creek Formation in Illinois, the Joggins Formation in Nova Scotia, and similar deposits worldwide contain fossils so well preserved that we can see individual muscle fibers, nerve cells, and even the contents of digestive systems. These fossil deposits reveal that Carboniferous giants weren't just larger versions of modern arthropods, they were fundamentally different organisms with capabilities that no modern arthropod possesses. Recent CT scanning and three-dimensional reconstruction of these fossils has revealed internal anatomies of startling complexity. But here's the twist that makes these Carboniferous giants even more remarkable. These weren't just larger arthropods. They were more intelligent, more sophisticated, and more specialized than any arthropods that had come before or have existed since. The combination of large body size and high oxygen levels allowed for the evolution of nervous systems of unprecedented complexity in invertebrate organisms. Meganeura, the giant dragonfly, had compound eyes with over 30,000 individual lenses, giving it visual capabilities that may have exceeded those of modern birds of prey. Each lens was larger and more sophisticated than those of modern dragonflies, with specialized photoreceptor cells and neural processing capabilities that approached vertebrate standards. Recent analysis of Meganeura brain fossils has revealed neural structures that were proportionally much larger than those of modern insects. The brain showed clear evidence of specialized regions for processing visual information, coordinating flight behavior, and integrating sensory inputs from multiple sources. This neural complexity would have allowed for sophisticated hunting behaviors, learning from experience, and even primitive forms of memory storage. The fossil evidence suggests that Meganeura was capable of complex aerial hunting strategies that required three-dimensional spatial reasoning, predictive tracking of moving prey, and precise coordination of flight muscles for rapid acceleration and maneuvering. These capabilities approached those of modern vertebrate aerial predators like hawks or eagles, but in an invertebrate body plan that was fundamentally different from anything we see today. But Meganeura was just one example of the neural sophistication that characterized Carboniferous giants. Arthropleura, the giant millipede, wasn't actually a predator. but its feeding behavior and environmental impact were so significant that it literally shaped the structure of Carboniferous forests in ways that no modern invertebrate can match. Recent isotope analysis of Arthropleura fossils has revealed that these giants were capable of processing enormous quantities of plant matter, potentially several times their own body weight daily. But more importantly, they were selective feeders, choosing specific plant species and plant parts based on nutritional content, toxicity levels, and digestibility. This selective feeding behavior required sophisticated chemosensory systems for evaluating plant chemistry, decision-making capabilities for choosing optimal feeding strategies, and memory systems for remembering the locations of preferred food sources. The neural complexity required for such behaviors approaches that of modern vertebrate herbivores. The reveal is that these Carboniferous giants weren't just successful predators, they were ecosystem engineers on a scale that's difficult to imagine. By processing enormous quantities of plant matter, Arthropleura created clearings in dense forest vegetation, modified soil chemistry through its waste products, and influenced the distribution and evolution of plant species across entire continents. Recent analysis of Carboniferous plant fossil assemblages has revealed that plant species diversity and distribution patterns were significantly influenced by giant arthropod feeding behavior. Some plant species appear to have evolved specific defensive strategies against giant arthropod herbivores, while others may have evolved to attract these giants as a means of seed dispersal. This level of ecosystem influence was unprecedented for invertebrate organisms and wouldn't be matched again until the evolution of large mammalian herbivores hundreds of millions of years later. The Carboniferous giants were essentially filling ecological roles that we now associate with elephants, rhinoceros, and other large mammals. We cannot know for certain how these giants interacted with each other, but the fossil evidence suggests complex ecological relationships that rivaled those of modern large mammal ecosystems. Some formations preserve evidence of what appear to be territorial disputes between giant arthropods, with fossilized remains showing battle damage that could only have come from encounters with other large predators. Recent analysis of bite marks and claw damage on Carboniferous arthropod fossils has revealed evidence of intraspecific violence that suggests sophisticated territorial and competitive behaviors. The patterns of damage indicate that these giants were capable of complex fighting strategies, using their size and specialized weaponry in coordinated attacks against rivals. Some fossils preserve evidence of what appear to be ritualized combat behaviors, with specific types of damage that suggest non-lethal territorial disputes rather than predatory attacks. This implies social complexity and behavioral sophistication that approaches that of modern vertebrates. The hunting strategies of Carboniferous predatory giants were unlike anything in the modern world. Pterygotus, a eurypterid that could reach lengths of over 2 meters, appears to have been an ambush predator that could remain motionless for extended periods before striking with incredible speed and precision. Biomechanical analysis of Pterygotus fossils has revealed muscle attachment points and joint structures that suggest it could accelerate from rest to attack speed in milliseconds, faster than most modern predators of comparable size. The power-to-weight ratio of its locomotor system exceeded that of modern crocodiles, despite being built on a fundamentally different body plan. Recent computer modelling of Pterygotus' attack behaviour has suggested that it may have been capable of launching itself partially out of water to capture terrestrial prey, a behaviour that would have made it one of the most versatile predators in Earth's history, equally capable of hunting in aquatic and terrestrial environments. The haunting question is, what was it like to be a smaller organism in a world dominated by these giants? The honest answer is that it was probably the most dangerous period in terrestrial history for anything that wasn't itself a giant arthropod. The fossil record from this period shows evidence of extreme predation pressure on smaller organisms. Every available ecological niche was under constant threat from giant predators with capabilities that no modern ecosystem contains. Small arthropods, early vertebrates, and other organisms developed increasingly sophisticated defensive strategies in response to this unprecedented predation pressure. Some smaller organisms developed elaborate armor systems, complex exoskeletons with spines, ridges, and specialized defensive structures that made them difficult for giant predators to handle. Others evolved chemical defenses, toxins and deterrent compounds that could poison or disable giant predators despite the size difference. Still others developed behavioral defenses that took advantage of the giant's limitations. speed and agility became premium survival traits, with smaller organisms evolving locomotor systems that allowed them to escape into spaces too small for giant predators to follow. Recent analysis of Carboniferous trace fossils has revealed evidence of complex predator-prey interactions that demonstrate the sophisticated behavioral strategies that evolved during this period. We see trackways that suggest coordinated group escape behaviors, evidence of chemical communication systems for warning of predator presence, and even what appear to be decoy strategies designed to misdirect giant predators. But perhaps most significantly, this period saw the evolution of the first truly effective anti-arthropod strategies among vertebrate animals. Early amphibians and reptiles began developing characteristics specifically adapted for competing with and eventually displacing arthropod predators. These vertebrate adaptations included stronger jaws capable of crushing arthropod exoskeletons, more efficient respiratory systems that maintained high performance even in varying oxygen levels, improved sensory capabilities for detecting giant arthropods, and behavioral strategies specifically designed for avoiding or countering arthropod attacks. Recent research has revealed that some Carboniferous arthropods were capable of learning and memory in ways that approach the capabilities of modern vertebrates. Trace fossils show evidence of modified hunting behavior over time, suggesting that individual predators could adapt their strategies based on experience and changing environmental conditions. This cognitive sophistication was unprecedented in invertebrate evolution. Some formations preserve evidence of what appear to be tool-use behaviors, with giant arthropods manipulating environmental objects to enhance their hunting effectiveness or modify their territories. Other fossils suggest that some giants were capable of social learning, acquiring new behaviors by observing the actions of other individuals rather than through individual trial and error. This would have allowed successful hunting strategies to spread rapidly through populations, creating cultural evolution within arthropod communities. The neural architecture required for such sophisticated behaviors approaches that of modern vertebrates in complexity, despite being built on a completely different organizational plan. The Carboniferous giants were demonstrating that intelligence and behavioral sophistication are not limited to vertebrate body plans. This cognitive sophistication, combined with their massive size and environmental dominance, made Carboniferous arthropods perhaps the most formidable predators in Earth's history. They were successful for over 50 million years, a reign of ecological dominance that lasted longer than the entire age of dinosaurs and was more complete in its control over terrestrial ecosystems. Recent analysis of Carboniferous ecosystem structure has revealed that giant arthropods controlled energy flow and nutrient cycling in ways that no modern terrestrial predators approach. They were simultaneously apex predators, primary ecosystem engineers, and keystone species whose activities determine the structure and function of entire continental ecosystems. Their influence extended beyond direct predation to include habitat modification, plant community structure, soil development, and even climate regulation, through their effects on vegetation patterns and atmospheric gas exchange. They were, in effect, the architects of terrestrial ecosystem structure during one of the most productive periods in Earth's history. And yet, their very success contained the seeds of their downfall. The high oxygen atmosphere that enabled their gigantism was inherently unstable, maintained by a delicate balance of geological and biological processes that was vulnerable to disruption. As atmospheric conditions began to change, these giants found themselves in an increasingly hostile world where their greatest adaptations became their fatal weaknesses. The end of the Carboniferous period brought atmospheric changes that would transform not just the giants themselves, but the entire structure of terrestrial ecosystems. Oxygen levels began to decline, temperature patterns shifted, and the lush forests that had supported giant arthropod communities began to give way to drier, more seasonal climates. But the decline of the giants wasn't simply a matter of environmental change. They faced increasing competition from vertebrate animals that had evolved specifically to exploit the ecological niches that giant arthropods had dominated for so long. Early reptiles and amphibians had developed physiological and behavioral adaptations that made them more efficient and adaptable than even the most sophisticated arthropod giants. So the question remains, if these giant arthropods were so successful, so well adapted and so dominant in their ecosystems for such a long period of time, what force could possibly have been powerful enough to bring about their decline and eventual replacement by vertebrate animals? The answer lies in understanding the fundamental differences between arthropod and vertebrate body plans, and how those differences became critical when Earth's environment began to change in ways that favoured flexibility and adaptability over size and specialisation. Chapter 11: The Great Collapse. When the air became poison for the giants, around 280 million years ago, something began to happen that would end the reign of the giant arthropods and fundamentally reshape life on Earth in ways that continue to influence ecosystems today. The atmosphere that had nurtured these monsters for tens of millions of years began to turn against them, and what had been their greatest evolutionary advantage became their fatal weakness in a planetary transformation that was both gradual and catastrophically sudden. It is strange to imagine, but the same high oxygen atmosphere that had allowed arthropods to grow to impossible sizes was inherently unstable, maintained by a complex web of geological, atmospheric, and biological processes that were vulnerable to disruption. Like a house of cards built from atmospheric chemistry, the entire system was precarious despite its apparent stability, and when it began to collapse, the effects were devastating beyond imagination. The evidence for this atmospheric collapse comes from multiple independent sources that all point to the same terrifying conclusion: ice core data from ancient glacial periods, isotope ratios in rocks and fossil shells, changes in plant fossil assemblages, and dramatic shifts in animal fossil records all indicate a rapid and severe reduction in atmospheric oxygen levels that began around 280 million years ago and continued for millions of years. Within what was, geologically speaking, a brief period, perhaps as little as a few million years, oxygen concentrations dropped from 35% to less than 15%, falling below modern atmospheric levels and creating conditions that were catastrophic for organisms adapted to the oxygen-rich world of the late Carboniferous period. Recent atmospheric modelling has revealed that this decline wasn't gradual or uniform. Instead, oxygen levels appear to have fluctuated dramatically, with periods of rapid decline followed by partial recovery, then further collapse. This pattern of instability would have been even more devastating for large organisms than a steady decline, because it prevented evolutionary adaptation to changing conditions. For giant arthropods, this atmospheric collapse was nothing short of catastrophic. Their respiratory systems, which had evolved to perfection in high oxygen environments, were fundamentally dependent on passive diffusion of gases through their tracheal networks. These systems worked magnificently when oxygen was abundant, but they failed completely when concentrations dropped below critical thresholds. The physics of gas diffusion meant that larger arthropods were disproportionately affected by declining oxygen levels. As body size increases, the distance that oxygen must travel to reach internal tissues increases much faster than the capacity of the respiratory system to deliver it. When oxygen concentrations dropped, the largest arthropods were the first to suffer respiratory failure. But here's the twist that makes this collapse even more tragic. This wasn't just about respiratory failure or simple suffocation. The decline in oxygen levels triggered a cascade of environmental changes that made survival impossible for large terrestrial arthropods, even beyond the direct effects of oxygen limitation. Lower oxygen levels meant less efficient metabolism for organisms that had evolved high-energy lifestyles dependent on abundant oxygen. Reduced metabolic efficiency meant decreased ability to maintain large body masses, reduced capacity for rapid movement and complex behaviours, and diminished effectiveness of hunting and defensive strategies that required high energy expenditure. Recent analysis of the fossil transition has revealed that the decline in oxygen also affected the atmospheric properties that giant arthropods had relied upon for sensory navigation. The density and chemical composition of the atmosphere changed in ways that altered sound transmission, scent diffusion, and even the optical properties of air, disrupting sensory systems that had evolved to function in the specific atmospheric conditions of the Carboniferous period. The reveal is that we can watch this catastrophe unfold in real time through the fossil record, like reading a geological crime novel where the victim and the murder weapon are both preserved in stone. Carboniferous fossil sites show abundant remains of giant arthropods in their earlier layers, but as we move up through the geological strata forward through time, these giants become increasingly rare, progressively smaller, and ultimately absent. It's like watching a slow-motion extinction event preserved in stone, with each layer of rock representing a chapter in the decline and fall of Earth's most successful invertebrate predators. The fossil evidence shows not just the end result of extinction, but the process itself, the gradual reduction in body size, the increasing rarity of giant specimens, and the eventual disappearance of entire lineages. Recent analysis of these fossil sequences has revealed that the decline wasn't uniform across all giant arthropod species. Some groups disappeared rapidly when oxygen levels first began to decline, while others persisted for millions of years in increasingly restricted habitats before finally succumbing to environmental change. The species that survived longest were generally those with the most efficient respiratory systems, the smallest body sizes within their groups, and the greatest behavioural flexibility. This suggests that evolution was attempting to respond to the changing conditions, but that the rate of environmental change ultimately exceeded the capacity of arthropod physiology to adapt. We cannot know for certain what it was like for individual giant arthropods during this transition, but the fossil evidence suggests it was a prolonged agony rather than rapid extinction. Some fossil sites preserve arthropods that appear to have died from respiratory failure, their bodies positioned in ways that suggest they were struggling to breathe, with their breathing apparatus extended and their bodies contorted in apparent distress. Other fossils show evidence of starvation and metabolic dysfunction. As oxygen levels declined and metabolic efficiency decreased, giant arthropods would have required increasingly large amounts of food to maintain their body functions, but their hunting efficiency would have declined simultaneously due to reduced energy availability for complex behaviours. Recent geochemical analysis has revealed that the atmospheric changes also affected food webs in ways that reduced prey availability for giant predators. Plant communities changed as atmospheric composition shifted, affecting the entire base of terrestrial food webs and reducing the productivity of ecosystems that had supported large predator populations. The haunting question is, why couldn't these sophisticated organisms adapt to the changing conditions? They had survived for tens of millions of years, demonstrating remarkable evolutionary success and adaptability. They had sophisticated nervous systems, complex behaviours, and evolutionary flexibility that had allowed them to dominate diverse environments across multiple continents. The honest answer is that they were victims of their own evolutionary success. Over millions of years of evolution in high oxygen environments, they had become so perfectly adapted to those specific conditions that they couldn't readjust when the fundamental parameters of their world changed. Their respiratory systems were too specialized for high oxygen conditions to function efficiently when oxygen levels declined. Their metabolisms were too dependent on abundant energy to maintain function when metabolic efficiency decreased. Their body sizes were too large to be supported by the energy budgets that were possible in low oxygen environments. Evolution had painted them into a corner from which there was no escape. The very adaptations that had made them so successful in the Carboniferous world became fatal liabilities when that world disappeared. They were like perfectly tuned racing cars that could achieve incredible performance on a specific type of track, but couldn't function at all when the track conditions changed. Recent analysis of the evolutionary relationships among Carboniferous arthropods has revealed that some lineages attempted evolutionary responses to the changing conditions. We see evidence of rapid evolution towards smaller body sizes, more efficient respiratory systems, and reduced energy requirements in some groups during the terminal Carboniferous period. But these evolutionary attempts were ultimately unsuccessful. The rate of environmental change was too rapid for evolutionary adaptation to keep pace. Populations that had spent millions of years adapting to high oxygen conditions couldn't evolve new physiologies quickly enough to survive in low oxygen environments. Some lineages appear to have survived for extended periods in refugial habitats, isolated environments where local conditions remained more similar to Carboniferous norms. But these refugia were eventually overwhelmed by global atmospheric changes, leading to the final extinction of giant arthropod lineages worldwide. But the collapse of the giant arthropods created opportunities for other organisms that had been waiting in the ecological shadows. As these apex predators disappeared, ecological niches opened up that would be filled by entirely different types of organisms, early reptiles, amphibians, and eventually the ancestors of dinosaurs and mammals. The transition wasn't immediate or smooth. Recent analysis of fossil assemblages from the Permian period has revealed several million years of ecological chaos as ecosystems reorganized following the collapse of arthropod-dominated food webs. Some regions became virtually lifeless as the careful balance of predator and prey relationships that had existed during the Carboniferous was shattered. During this transition period, some environments were characterized by what paleontologists call ecological release, the rapid diversification of surviving groups into niches that had been previously occupied by extinct giants. Small arthropods, early vertebrates, and other organisms suddenly found themselves without competition from giant predators and rapidly diversified to fill available ecological roles. Recent research has revealed that this period of ecological reorganization saw one of the most dramatic reshufflings of ecosystem structure in Earth's history. Organisms that had been minor components of Carboniferous ecosystems suddenly found themselves as dominant players in post-collapse environments. Early reptiles and amphibians in particular benefited enormously from the disappearance of giant arthropod predators. These vertebrates had respiratory and circulatory systems that were more efficient in low-oxygen environments than arthropod respiratory systems. They could not only survive the new atmospheric conditions, they could thrive in them. Recent physiological modelling has revealed that vertebrate cardiovascular systems with active circulation of oxygen-carrying blood maintain high efficiency across a wider range of atmospheric oxygen concentrations than arthropod tracheal systems. This gave vertebrates a crucial advantage during the atmospheric transition. The implications of this atmospheric crisis extend far beyond the fate of giant arthropods. This event demonstrated that even the most successful, well-adapted and dominant organisms could be vulnerable to environmental changes that occurred faster than evolution could respond. It also marked the beginning of vertebrate dominance on land that continues to this day. The physiological advantages that allowed early reptiles and amphibians to survive the oxygen crisis would eventually lead to the evolution of dinosaurs, mammals, and ultimately humans. But perhaps most importantly, the collapse of the Carboniferous giants revealed fundamental truths about the nature of evolutionary success and the relationship between organisms and their environment. Success in one set of environmental conditions doesn't guarantee survival when those conditions change, and the most specialized organisms are often the most vulnerable to environmental disruption. And yet, the most haunting aspect of this collapse wasn't the extinction of the giants. It was what their disappearance revealed about the fragility of ecological stability. These arthropods had ruled Earth's terrestrial ecosystems for over 50 million years, longer than any other group of large land predators in Earth's history. They had seemed invincible, permanent features of the terrestrial landscape. Their sudden vulnerability to atmospheric change demonstrated that no evolutionary strategy, no matter how successful or long-lived, is permanent. The very traits that make organisms successful in one environment can become fatal liabilities when conditions change, and the history of life is ultimately a story of repeated environmental challenges that test the limits of biological adaptability. Recent analysis of extinction patterns throughout Earth's history has revealed that the collapse of Carboniferous giants was not unique. It was part of a recurring pattern where dominant organisms are displaced by environmental changes that favour different physiological and ecological strategies. So the question remains, if even the most successful predators in Earth's history could be undone by environmental change, what lessons does their collapse hold for understanding the rise of the vertebrate predators that would eventually replace them? And how did the survivors of this atmospheric catastrophe lay the foundation for the age of reptiles, dinosaurs and mammals that would follow? The answer lies in understanding the fundamental differences between arthropod and vertebrate body plans, and how those differences became critical advantages when Earth's environment shifted in ways that rewarded adaptability over specialization, efficiency over optimization, and physiological flexibility over perfect adaptation to specific conditions. Chapter 12. The Dawn of the Vertebrates. The New Lords of Terra. Around 250 million years ago, as the last of the giant arthropods vanished from terrestrial ecosystems, something unprecedented emerged to take their place. Vertebrate predators with capabilities that would make the age of arthropod supremacy seem almost primitive. The world was changing, and the throne of terror, once held by scuttling armored giants, was about to be seized by creatures with bones, blood, and brains unlike anything Earth had ever seen. There is a moment in the fossil record when you can see the torch being passed from one evolutionary dynasty to another. The layered rocks tell a story of transition. Giant arthropod remains becoming scarce, and then disappearing entirely, while simultaneously vertebrate fossils multiply, diversify, and grow more sophisticated. It is as if the Earth itself had decided that one reign of horror had ended, and a new, more terrifying chapter was about to begin. And these weren't the clumsy experimental vertebrates of earlier eras, the small amphibians struggling at the water's edge, or the fragile reptiles barely capable of dominating their prey. These were organisms that had learned from the evolutionary lessons of their arthropod predecessors and had pushed beyond them, developing predatory capacities that surpassed anything the Carboniferous or Permian had ever produced. The early archosaurs, ancestors of dinosaurs, crocodiles, and eventually birds, represented a revolution. They possessed something arthropods had never achieved: truly efficient respiratory systems. While arthropods had relied on the passive diffusion of oxygen through tracheae or gills, vertebrates had evolved active circulation. They had muscular pumps to move air and blood, four-chambered hearts to keep oxygen-rich and oxygen-poor blood separated, and vascular systems capable of delivering oxygen precisely where it was needed, when it was needed. They were not prisoners of atmospheric conditions. They were masters of their own biology. But here's the twist. These new predators didn't merely replace the ecological roles of giant arthropods. They transcended them. They could grow larger without collapsing under their own weight, move faster without exhausting their bodies, think more complexly, and hunt with strategies that had never before been possible on land. They were predators not just in form but in mind. The revelation of vertebrate supremacy lies in their ability to regulate their internal environment. Arthropods, encased in rigid exoskeletons, had been bound to the external world, their physiology tied to atmospheric oxygen levels, their size capped by diffusion limits. Vertebrates, with their skeletons on the inside, their muscles anchored to bones, their organs maintained in tightly controlled environments, could transcend those limitations. They were no longer bound by air density, by external humidity, by the physics of exoskeletons. They were free to expand into sizes, behaviors, and strategies that arthropods could never approach. We cannot reconstruct every detail of the landscapes these creatures first dominated, but the fossil evidence suggests a period of extraordinary innovation. The ecosystems of the Triassic were undergoing rebirth after the devastation of the Permian extinction, the deadliest event in Earth's history. The stage was open. Plants were reclaiming land, insects buzzing back to abundance, herbivorous reptiles spreading across the continents. Into this recovering world stepped predators like Erythrosaucus, one of the most terrifying hunters of its time. Erythrosaucus, prowling southern Pangaea around 245 million years ago, reached over 4 meters in length. With its massive skull, serrated teeth, and sprawling but powerful limbs, it was a predator that dwarfed anything left of the arthropod lineages. It combined size with an active metabolism, sophisticated sensory systems, and a behavioral flexibility no invertebrate nervous system could ever match. This was not simply a larger predator. It was a predator capable of reacting, adapting, and learning in real time. The haunting question is why vertebrate predators were so much more effective than their arthropod predecessors. The answer lies deep in body plans. Arthropods had armor, claws, and numbers, but their nervous systems were decentralized, limited in capacity. Their respiratory systems constrained them to modest levels of activity, and their rigid exoskeletons imposed a maximum size they could never break. Vertebrates, by contrast, had internal skeletons that could support enormous bodies without collapse. They had circulatory systems that could maintain activity for hours. And most importantly, they had brains, large, complex and plastic organs capable of storing memories, processing sensory information, and generating new strategies. This mental leap transformed predation. Recent research suggests that some early archosaurs already displayed social behaviors, group movement, coordinated attacks, even the possibility of cooperative hunting. These were not just brute killers, but intelligent ones, predators that could anticipate prey movement, adjust their strategies, and exploit weaknesses with terrifying efficiency. Fossil trackways and bone beds hint at group hunts, predators working together to drive prey into ambushes, much as wolves or lions do today. The fossil record preserves scenes of predatory innovation that arthropods could never match. Some archosaurs specialized in pursuit, their long legs and high endurance allowing them to chase prey for kilometers until exhaustion made escape impossible. Others mastered ambush, lurking motionless in swamps or river margins until the perfect moment, striking with explosive speed. Still others seem to have experimented with ecological manipulation, selective predation that may have influenced the abundance and recovery of certain herbivores. The implication is staggering. Vertebrate predators may have been managing ecosystems in ways that hinted at ecological reasoning, a step beyond instinct, a step towards strategy. This represents a fundamental shift. Where arthropods had been bound by their environment, vertebrates began to shape theirs. With strength, mobility, and intelligence, they bent ecosystems around themselves. Prey were no longer simply victims, they were forced into evolutionary innovation. Armor, spines, speed, camouflage, even herd behavior. Many of these responses were born in this crucible of vertebrate predation. The world itself began to change under the pressure of their existence. And yet, even as vertebrate predators seized control of the land, something even more dramatic was happening in the oceans. The seas, once dominated by armored fish and invertebrate hunters, were now becoming laboratories of vertebrate innovation as well. Marine reptiles began to appear, ichthyosaurs streamlined like dolphins, plesiosaurs with long necks and gaping jaws, and later mosasaurs that would grow to titanic lengths. Compared to these leviathans, even the most formidable land predator seemed small. The evolutionary arms race had expanded into the oceans with creatures that pushed biology to its extremes. What makes this transition so haunting is its permanence. The age of giant arthropods ended forever with the rise of vertebrate dominance. Never again would invertebrates rule the land as apex predators. They remained important, of course. Insects and spiders became ubiquitous, but they would never reclaim the throne. The vertebrates had seized it, and they would never let go. By the mid-Triassic, the outlines of a new world were clear. Archosaurs were diversifying rapidly, some becoming herbivores, others small insectivores, but many refining their role as apex hunters. Their descendants would dominate for the next 150 million years, evolving into the terrifying predators of the Jurassic and Cretaceous, allosaurs, tyrannosaurs, raptors with sickle claws and pack tactics. The seeds of that dynasty were planted in these early days, when the first vertebrate predators showed what bones, blood and brains could do when combined with hunger. The rise of vertebrate predators is not just the story of new hunters appearing, it is the story of intelligence and physiology breaking through old limits. Internal skeletons meant growth without collapse. Circulatory systems meant endurance without exhaustion. Brains meant strategy without limit. These were not simply animals, they were systems designed for conquest. And so the question that echoes through deep time remains. If terrestrial vertebrates so quickly surpassed the achievements of the greatest arthropods, what would happen when vertebrate evolution turned fully to the oceans, where size, buoyancy and opportunity had no upper limit? The answer would come in the form of oceanic monsters so vast and sophisticated they would redefine the meaning of predator itself. The catastrophe that ended the age of dinosaurs was also the beginning of the age of mammals, the evolutionary radiation that would eventually lead to human consciousness and our ability to contemplate the deep history of life on Earth. We are, in a very real sense, the heirs of that ancient catastrophe, existing because a rock from space ended one evolutionary experiment and began another. Recent research into the immediate aftermath of the extinction has revealed that recovery wasn't quick or simple. For nearly 10 million years after the impact, terrestrial ecosystems remained simplified and relatively low in diversity compared to what had existed before. The complex ecological relationships and sophisticated behaviours that had characterised Cretaceous communities took millions of years to re-evolve in different forms. But when recovery finally occurred, it led to innovations that the dinosaur-dominated world had never achieved. The mammals that inherited the Earth would eventually develop forms of intelligence, social organisation, and environmental manipulation that exceeded even the most sophisticated dinosaur achievements. The survivors of the Great Catastrophe carried forward not just their own evolutionary potential, but the lessons learned from 160 million years of dinosaur innovation. The predatory strategies, ecological relationships, and behavioural sophistications that had been perfected during the age of dinosaurs would be incorporated into new evolutionary experiments that would ultimately lead to the complex ecosystems we know today. So, the question remains, as we reach the end of our journey through the most terrifying chapters of Earth's prehistoric past, what lessons do these ancient catastrophes and recoveries hold for understanding the nature of life itself, and how the ultimate horror of extinction can paradoxically become the foundation for unprecedented evolutionary opportunity? The answer lies in recognizing that the story of prehistoric terror we've explored together isn't just about ancient monsters and vanished worlds. It's about the fundamental processes that have shaped all life on Earth, including our own existence, and continue to operate in the world around us today. Every breath we take, every thought we think, every moment of consciousness we experience exists because of the long chain of catastrophes, recoveries, innovations, and extinctions that we've traced through deep time. The prehistoric terrors that once ruled Earth are gone, but their legacy lives on in the complex ecosystems, sophisticated behaviors, and incredible diversity of life that surrounds us. We are not separate from this ancient history of horror and wonder. We are its culmination, its current expression, and its continuation into an unknowable future. Chapter 13: The Silent Survivors. The refugees of horror in the post-collapse world around 250 million years ago, as the dust settled from the greatest extinction event in Earth's history and the last of the Carboniferous giants faded into memory, something extraordinary happened in the hidden corners of our planet. Life didn't simply recover from the devastation. It learned to hide, to adapt, and to survive in ways that would ensure it could endure whatever catastrophes the future might bring. There is a moment in the fossil record when you realize that extinction events don't just end stories, they begin new ones. In the aftermath of the Permian-Triassic extinction, which eliminated up to 96% of marine species and 70% of terrestrial vertebrates, the survivors weren't just lucky, they were revolutionary in their approach to existence itself. It is strange to imagine, but the most successful survivors of Earth's greatest catastrophe weren't the largest, strongest, or most sophisticated organisms. They were the small, the flexible, and the hidden, creatures that had learned to thrive in the spaces between worlds, in the cracks and crevices that the giants had ignored. Recent analysis of post-extinction fossil assemblages has revealed that survival wasn't random. The organisms that made it through the Great Dying shared specific characteristics that would prove crucial not just for surviving extinction, but for inheriting the Earth that would emerge from the ashes of the Old World. The evidence suggests that the first and most important survival strategy was miniaturization. In a world where resources had become scarce and environmental conditions were unstable, being small became a tremendous advantage. Small organisms required less food, could survive in marginal habitats, and could reproduce quickly when conditions improved. But here's the twist that makes these post-extinction survivors so remarkable. They weren't just smaller versions of pre-extinction organisms, they had evolved entirely new approaches to survival that would prove more effective than anything the giants had achieved during their millions of years of dominance. Recent research has revealed that many post-extinction survivors had evolved what we might call stealth biology, the ability to remain virtually undetectable while still maintaining all the functions necessary for survival and reproduction. These weren't organisms in hiding. They were organisms that had evolved to be invisible. Some developed biochemical camouflage that made them chemically indistinguishable from their environment. Others evolved behavioral patterns that allowed them to avoid detection by remaining motionless for extended periods, becoming active only when environmental conditions guaranteed their safety. The reveal is that these survival strategies weren't temporary adaptations to post-extinction conditions. They were permanent evolutionary innovations that would prove crucial for surviving future environmental catastrophes throughout Earth's history. We cannot know for certain what life was like for these early survivors, but the fossil evidence suggests they inhabited a world that was simultaneously emptier and more dangerous than anything that had existed before the Great Extinction. The ecological niches that had been filled by millions of species for hundreds of millions of years were suddenly vacant, creating both opportunities and unprecedented challenges. Recent analysis of trace fossils from this period has revealed evidence of behavioral innovations that were impossible during the crowded ecosystems of the pre-extinction world. Some survivors began exploiting resources that had never been used before, developing entirely new metabolic pathways and ecological strategies. Others began forming new types of ecological relationships, symbioses and partnerships that would have been unnecessary or impossible when resources were abundant and competition was intense. These new relationships often involved species that had never interacted before the extinction, creating hybrid ecosystems that were unlike anything in the fossil record. But perhaps most significantly, some survivors began developing what we might call extinction resistance, biological and behavioral adaptations specifically designed to survive future catastrophic events. These organisms had learned from the Great Dying and were preparing for the next one. Recent molecular analysis has revealed that many modern extremophiles, organisms that can survive in conditions that would be lethal to most life, trace their origins to these post-extinction survivors. The ability to survive extreme temperatures, toxic chemical conditions, and resource scarcity that characterizes these modern organisms was first developed during the recovery from the Permian-Triassic extinction. The haunting question is, what does it mean for life to prepare for extinction? These survivors weren't just adapting to their current environment, they were adapting to the possibility that their environment might disappear entirely. They were evolution's insurance policy against catastrophe. Recent research has revealed that some of these organisms developed what appears to be genetic redundancy, multiple copies of essential genes that could continue functioning even if some were damaged by environmental catastrophe. Others evolved modular biology, cellular and physiological systems that could shut down non-essential functions during crisis periods while maintaining core survival capabilities. But the most remarkable adaptation was the evolution of rapid recovery systems, biological mechanisms that allowed survivors to quickly exploit new opportunities when they became available. These organisms could remain dormant during adverse conditions and then reproduce explosively when conditions improved. The honest answer is that we're still discovering the full extent of how these post-extinction survivors changed the rules of life on Earth. Recent genetic analysis of modern organisms has revealed that many of the most important biological innovations we see today, from advanced immune systems to sophisticated stress responses, trace their origins to adaptations that first evolved during the post-extinction recovery period. And yet, these survivors face challenges that went beyond simple resource scarcity or environmental instability. They were inheriting a world where the fundamental rules of ecological organization had been shattered, where the biological relationships that had structured ecosystems for hundreds of millions of years no longer existed. Some survivors responded by becoming extreme generalists, organisms capable of exploiting virtually any available resource and surviving in almost any environment. Others became extreme specialists, focusing on narrow ecological niches that were likely to remain stable, even during environmental catastrophe. Recent analysis of evolutionary rates during this period has revealed that biological innovation was occurring at unprecedented speeds. The empty ecological landscape created by the extinction provided opportunities for rapid evolutionary experimentation that led to new body plans, new metabolic strategies, and new ecological relationships. This period of rapid evolution would lay the foundation for all subsequent life on Earth. The survivors of the Great Extinction would give rise to the dinosaurs, the first mammals, the ancestors of modern marine ecosystems, and ultimately the lineages that would lead to human consciousness. So the question remains, if these small hidden survivors could inherit the Earth from the greatest predators and most sophisticated ecosystems in history, what does their success tell us about the nature of survival itself, and how their innovations would set the stage for the next great chapter in the evolution of terror? Chapter 14, The New Generation of Monsters. The dawn of the predatory dinosaurs. Around 230 million years ago, something emerged from the evolutionary laboratories of post-extinction Earth that would redefine what it meant to be a terrestrial predator. These weren't the failed experiments or temporary adaptations of a world struggling to recover. These were purpose-built killing machines that combined the best innovations from hundreds of millions of years of predatory evolution into forms that were more efficient, more intelligent, and more terrifying than anything that had come before. There is a moment in the fossil record when you can see evolution making a quantum leap forward. In the Middle Triassic formations of Argentina, Germany, and other locations around the world, we find the remains of the first true dinosaurs, and many of them were predators that represented a completely new approach to terrestrial hunting. It is strange to imagine, but the first dinosaurs weren't the massive lumbering giants that dominated later periods. They were relatively small, agile, intelligent predators that had solved problems that had challenged terrestrial hunters for hundreds of millions of years. They had evolved solutions to the fundamental constraints that had limited the effectiveness of earlier predatory species. The evidence suggests that early dinosaur predators like Euraptor and Herrerasaurus weren't just successful hunters. They were evolutionary breakthroughs that demonstrated entirely new possibilities for vertebrate predation. Recent biomechanical analysis has revealed capabilities that no previous terrestrial predator had achieved. Recent studies of dinosaur locomotion have revealed that even the earliest dinosaurs had evolved bipedal movement systems that were more efficient than anything that had existed before. Their hip structure, leg bone proportions and muscle arrangements allowed for sustained high-speed pursuit, rapid acceleration, and precise maneuvering that gave them overwhelming advantages over their prey. But here's the twist that makes early dinosaur predators truly revolutionary. They weren't just faster or stronger than earlier predators, they were smarter. Recent analysis of dinosaur brain cases has revealed neural complexity that approached that of modern birds, with specialized regions for processing visual information, coordinating complex movements, and integrating sensory data from multiple sources. This cognitive sophistication allowed early dinosaurs to develop hunting strategies that were impossible for earlier predators. They could plan attacks, coordinate group hunts, and adapt their tactics in real time based on prey behavior. They were the first terrestrial predators capable of true strategic thinking. Recent research has revealed that some early dinosaurs were already showing evidence of social hunting behaviors that rivaled those of modern mammalian pack hunters. Trackway evidence from Argentina and other locations shows multiple dinosaurs moving together in coordinated formations, suggesting sophisticated communication and tactical coordination. The reveal is that dinosaur predators didn't just dominate through size or strength. They dominated through intelligence, efficiency, and behavioral sophistication that was unmatched by any previous terrestrial predators. They represented a new level of predatory evolution that would prove so successful that it would persist for over 160 million years. We cannot know for certain what it was like to be prey in a world where dinosaur predators were beginning to establish their dominance, but the fossil evidence suggests it was unlike anything that had existed during earlier periods of Earth's history. These predators combined size, speed, intelligence, and behavioral sophistication in ways that created unprecedented challenges for survival. Recent analysis of prey species from early dinosaur-dominated ecosystems has revealed rapid evolutionary changes in defensive strategies. Prey animals developed thicker armor, faster running speeds, more sophisticated sensory systems, and behavioral adaptations that suggest intense predation pressure from intelligent, coordinated hunters. Some prey species evolved into the first truly large herbivores, organisms like the early sauropod ancestors that used size as their primary defense against dinosaur predators. Others developed advanced warning systems, herd behaviors, and cooperative defense strategies that allowed smaller animals to survive in a world dominated by intelligent pack hunters. But perhaps most significantly, some prey species began developing intelligence of their own. The predation pressure from early dinosaurs appears to have driven the evolution of cognitive capabilities in prey species that had never existed before in terrestrial ecosystems. Recent analysis of early mammal fossils from this period has revealed brain structures that suggest sophisticated behavioral capabilities, the ability to learn from experience, modify behavior based on predator presence, and even engage in primitive forms of tactical deception to avoid capture. The honest answer is that dinosaur predators created the first truly intelligent terrestrial ecosystems, environments where both predators and prey were engaged in cognitive arms races that drove the evolution of increasingly sophisticated behaviors and strategies. Recent research has revealed that early dinosaur ecosystems were characterized by unprecedented behavioral complexity. We see evidence of coordinated group hunting, sophisticated territorial behaviors, complex social structures, and even primitive forms of culture, the transmission of learned behaviors between individuals and across generations. The haunting question is, what made dinosaur predators so much more successful than the sophisticated predators that had come before them? Recent comparative analysis has revealed that dinosaurs combined advantages that had never been unified in a single group of organisms. They had the metabolic efficiency of advanced vertebrates, allowing them to maintain high activity levels for extended periods. They had sophisticated nervous systems that could process complex information and coordinate elaborate behaviors. They had skeletal and muscular systems that were optimized for both speed and power. Most importantly, they had behavioral flexibility that allowed them to adapt their hunting strategies to different prey species and environmental conditions. Recent biomechanical modeling has revealed that dinosaur predators were capable of hunting strategies that were impossible for earlier terrestrial predators. They could pursue prey over long distances, coordinate attacks across large areas, and adapt their tactics based on real-time assessment of prey behavior and environmental conditions. But the most terrifying aspect of dinosaur predators wasn't their individual capabilities, it was their potential for continued evolution. Unlike earlier predatory groups that had reached apparent evolutionary dead ends, dinosaurs represented a body plan and behavioral framework that could continue evolving and improving indefinitely. The fossil record shows that dinosaur predators continued to innovate throughout their 160 million year reign. They evolved larger sizes, more sophisticated hunting strategies, more efficient metabolisms, and more complex social behaviors. They never stopped getting better at what they did. Recent analysis of dinosaur diversity patterns has revealed that predatory dinosaurs were constantly experimenting with new approaches to hunting. Some evolved into pursuit specialists optimized for chasing fast-moving prey. Others became ambush specialists designed for explosive attacks on large herbivores. Still others developed into pack hunters capable of taking down prey much larger than any individual predator. And yet, even as dinosaur predators were establishing their dominance on land, they were also beginning to explore new environments and new forms of predation. Some dinosaurs returned to aquatic environments, becoming marine predators that rivaled the great marine reptiles. Others took to the air, becoming the first vertebrate aerial predators capable of true-powered flight. The implications of dinosaur success extend far beyond paleontology. The cognitive and behavioral innovations that first appeared in early dinosaur predators would eventually lead to the evolution of modern birds, which represent the direct descendants of theropod dinosaurs, and continue to demonstrate many of the predatory innovations that first appeared over 200 million years ago. So the question remains, if dinosaur predators were so successful, so adaptable, and so capable of continued evolutionary innovation, what could possibly have been powerful enough to end their reign and create opportunities for the mammalian predators that would eventually follow them? Chapter 15: The Kingdom of the Air. The first lords of the sky. Around 150 million years ago, something happened that changed the fundamental nature of predation on Earth forever. For the first time in the planet's history, sophisticated predators took to the skies, transforming the three-dimensional space above terrestrial ecosystems into hunting grounds that no prey species could escape. There is a moment when you realize that the evolution of flight wasn't just about transportation or escape, it was about creating an entirely new dimension of terror. In the skies above the late Jurassic world, pterosaurs and the first flying dinosaurs were pioneering forms of aerial predation that would make the ground-based hunters of earlier periods seem limited by comparison. It is strange to imagine, but the conquest of the air required solving engineering problems that were far more complex than anything terrestrial predators had ever faced. Flying predators had to master aerodynamics, develop lightweight but strong skeletal systems, evolve sophisticated navigation capabilities, and coordinate three-dimensional hunting strategies while maintaining the speed and precision necessary for successful predation. The evidence for early aerial predators comes from some of the most spectacular fossils ever discovered. The Solnhofen limestone of Germany, the Yohol biota of China, and similar formations around the world preserve flying reptiles and early birds in exquisite detail, revealing the anatomical and behavioral innovations that made aerial predation possible. Recent analysis of pterosaur fossils has revealed that these ancient flying reptiles weren't just reptiles with wings. They were highly specialized aerial predators, with adaptations that wouldn't be matched until the evolution of modern birds. Their hollow bones, specialized flight muscles, and sophisticated wing membranes represented some of the most advanced biological engineering in Earth's history. But here's the twist that makes early aerial predators even more remarkable. They didn't just adapt existing predatory strategies for aerial use, they invented entirely new forms of hunting that were impossible for terrestrial predators. They could strike from above without warning, pursue prey across vast distances, and exploit resources that were completely inaccessible to ground-based hunters. Recent biomechanical analysis has revealed that large pterosaurs like Quetzalcoatlus had hunting capabilities that approached those of modern fighter aircraft. With wingspans exceeding 10 meters and sophisticated flight control systems, they could soar at high altitudes for hours, survey vast territories for prey, and execute precision strikes with devastating effectiveness. The reveal is that aerial predators didn't just add a new hunting strategy to existing ecosystems, they fundamentally restructured the relationship between predators and prey across entire continents. For the first time, no terrestrial habitat was safe from predation, and no prey species could rely on distance or terrain for protection. We cannot know for certain what it was like to live in a world where predators ruled the skies, but the fossil evidence suggests it created evolutionary pressures unlike anything that had existed before. Prey species were forced to develop defenses against attacks that could come from any direction, at any time, often with little or no warning. Recent analysis of late Jurassic ecosystems has revealed that the evolution of aerial predators triggered rapid changes in prey behavior and ecology. Many species developed more sophisticated hiding behaviors, spending more time in dense vegetation or underground burrows where aerial predators couldn't reach them. Others evolved enhanced sensory systems specifically designed for detecting aerial threats. Improved vision for spotting approaching flying predators, better hearing for detecting the sound of wings, and even primitive forms of echolocation for navigating in darkness when aerial predators were less active. Recent research has revealed that some prey species began forming new types of social groups specifically designed for aerial predator defense. These weren't just simple herds or flocks, they were sophisticated early warning networks where individuals took turns watching the sky, while others fed or rested. But perhaps most significantly, some prey species began developing their own flight capabilities as an escape strategy. The evolution of flight in insects, birds, and even some mammals appears to have been driven largely by predation pressure from aerial predators, rather than by other factors like resource access or migration. The honest answer is that aerial predators created the first truly three-dimensional ecosystems on Earth, environments where predatory and defensive strategies had to account for vertical as well as horizontal space. This added complexity drove evolutionary innovation at rates that were unprecedented in terrestrial ecosystems. Recent analysis of pterosaur diversity has revealed that aerial predators rapidly diversified into specialized ecological roles. Some became high-altitude soaring specialists that could patrol vast territories in search of carrion or vulnerable prey. Others evolved into low-altitude pursuit specialists designed for chasing fast-moving aerial prey through complex terrain. Still others developed into aquatic specialists that combined flight with sophisticated diving capabilities, allowing them to exploit marine resources while maintaining the advantages of aerial mobility. These flying fishers could cover enormous distances in search of productive fishing areas and could access resources that were unavailable to purely terrestrial or purely aquatic predators. The haunting question is, how did aerial predators coordinate their hunting strategies in three-dimensional space? Recent research has revealed evidence of sophisticated navigation and communication systems that allowed flying predators to maintain contact with each other across vast distances. Some pterosaurs appear to have developed echolocation capabilities that allowed them to hunt in darkness or poor visibility conditions. Others evolved sophisticated visual systems with specialized brain regions for processing three-dimensional spatial information and tracking multiple moving targets simultaneously. Recent analysis of pterosaur social behavior has revealed evidence of coordinated group hunting strategies that required remarkable levels of aerial coordination. Some formations preserve evidence of multiple pterosaurs working together to herd fish into shallow water or to overwhelm large terrestrial prey through coordinated attacks from different directions. But the most terrifying aspect of aerial predators was their potential for continued evolutionary innovation. Unlike terrestrial predators that were constrained by the need to move across solid surfaces, aerial predators could continue evolving toward greater size, speed, and sophistication without encountering the same physical limitations. Recent research has revealed that the largest pterosaurs were approaching the theoretical limits of biological flight, with wingspans and body masses that represented the maximum possible for powered flight using biological materials. They were living aircraft that pushed the boundaries of what biology could achieve. And yet, even as pterosaurs were reaching these impressive sizes and capabilities, they were facing competition from a new group of aerial predators that would eventually surpass them. The first birds, direct descendants of theropod dinosaurs, were beginning to develop flight capabilities that combined the aerial innovations of pterosaurs with the behavioral sophistication of dinosaur predators. Recent analysis of early bird fossils has revealed that the first flying dinosaurs weren't just feathered reptiles. They were aerial predators with capabilities that exceeded those of pterosaurs in several key areas. They had more efficient flight systems, more sophisticated nervous systems, and behavioral flexibility that allowed them to exploit aerial resources more effectively. The competition between pterosaurs and early birds would drive both groups to ever greater levels of aerial sophistication, creating some of the most advanced flying organisms in Earth's history. and establishing aerial predation as a permanent and crucial component of terrestrial ecosystems. So the question remains, if aerial predators could achieve such remarkable sizes and capabilities, and if they had access to three-dimensional hunting grounds that terrestrial predators couldn't exploit, what factors would eventually limit their success and create opportunities for different types of predators to dominate future ecosystems? Chapter 16: The Great Final Hunt. The last act of the dinosaurs. Around 70 million years ago, during the final act of the Cretaceous period, something extraordinary was happening in Earth's ecosystems that would represent both the pinnacle and the end of the most successful predatory dynasty in terrestrial history. The dinosaur predators that had dominated land ecosystems for over 160 million years were reaching levels of size, sophistication, and ecological dominance that would never be equaled by any subsequent group of terrestrial hunters. There is a moment in the fossil record when you can see evolution pushing the boundaries of what vertebrate predators could accomplish. In the formations of Western North America, Mongolia, and other regions around the world, we find evidence of predatory dinosaurs that had achieved capabilities that seem almost impossible by modern standards. It is strange to imagine, but the final phase of dinosaur evolution wasn't a period of decline or stagnation. It was an era of unprecedented innovation and achievement. The late Cretaceous predators like Tyrannosaurus rex, Giganotosaurus and Carcharodontosaurus weren't just large dinosaurs, they were the culmination of over 160 million years of predatory evolution, representing the theoretical limits of what terrestrial hunters could achieve. Recent biomechanical analysis has revealed that these final dinosaur predators possessed capabilities that exceeded those of any terrestrial predator before or since. Tyrannosaurus rex, for example, combined crushing bite forces that could exceed 60,000 newtons with sophisticated sensory systems, advanced cognitive capabilities, and behavioral flexibility that approached that of modern intelligent mammals. The evidence suggests that late Cretaceous ecosystems were characterized by predatory sophistication that was unmatched in Earth's history. These weren't just individual super-predators, they were components of ecological systems where predation had reached levels of complexity and efficiency that would define the theoretical maximum for terrestrial ecosystems. But here's the twist that makes these final dinosaur predators even more remarkable. They weren't just individually impressive, they were engaged in ecological relationships and competitive dynamics that pushed the entire concept of predation to its evolutionary limits. Recent research has revealed that late Cretaceous North America supported multiple species of giant predatory dinosaurs simultaneously, each occupying slightly different ecological niches and hunting strategies. This level of large predator diversity was unprecedented and would never be equaled in subsequent terrestrial ecosystems. The reveal is that these final dinosaur communities represented the ultimate expression of predatory evolution. Ecosystems where multiple apex predators coexisted through sophisticated niche partitioning, behavioral specialization, and ecological innovations that maximized the efficiency of energy transfer through complex food webs. We cannot know for certain what it was like to live in these ultimate predatory ecosystems, but the fossil evidence suggests they were simultaneously the most dangerous and most efficiently organized terrestrial communities in Earth's history. Every ecological role was filled by highly specialized organisms that had been refined through millions of years of evolutionary competition. Recent analysis of late Cretaceous herbivore fossils has revealed that prey species had evolved defensive capabilities that matched the sophistication of their predators. Giant ceratopsians like Triceratops had developed armor and weapons that could effectively defend against even the largest predators. Hadrosaurs had evolved complex social behaviors and early warning systems that allowed them to detect and escape from approaching threats. The arms race between these ultimate predators and their prey had driven both groups to levels of specialization that represented the theoretical limits of their respective evolutionary strategies. Neither predators nor prey could become more effective without fundamental changes to their basic body plans and ecological approaches. Recent research has revealed that some late Cretaceous predators were beginning to show evidence of cultural behaviors, the transmission of learned hunting strategies between individuals and across generations. Some formations preserve trackway evidence that suggests experienced hunters were teaching younger individuals specific techniques for hunting particular prey species. Others show evidence of coordinated hunting strategies that required sophisticated communication and tactical planning. Multiple Tyrannosaurus individuals appear to have worked together to hunt large herbivores, coordinating their attacks to maximize success rates and minimize energy expenditure. But perhaps most significantly, some late Cretaceous predators were beginning to show evidence of what we might call ecological management, behaviors that influenced prey populations in ways that optimized long-term hunting success rather than simply maximizing short-term kills. The honest answer is that late Cretaceous predatory ecosystems had achieved a level of sophistication and efficiency that approached theoretical limits for biological systems. They were the most successful predatory communities in Earth's history, supporting the largest terrestrial predators, the most complex ecological relationships, and the most efficient energy transfer systems that biology had ever achieved. Recent analysis of ecosystem productivity during this period has revealed that late Cretaceous communities were supporting biomass concentrations that exceeded those of any subsequent terrestrial ecosystems. The combination of warm global climate, high atmospheric carbon dioxide levels, and highly evolved predator-prey relationships created conditions that maximized biological productivity. The haunting question is, if these ultimate predatory ecosystems were so successful, so well adapted, and so efficiently organized, what could possibly have been powerful enough to destroy them completely? Recent research has revealed that the success of late Cretaceous ecosystems may have actually made them more vulnerable to catastrophic disruption. Their high level of specialization and efficiency meant that they were highly dependent on stable environmental conditions and complex ecological relationships that could be easily disrupted by environmental change. The giant predators that were the apex of terrestrial evolution were also the most vulnerable to any disruption in their food webs. Their enormous size and high metabolic demands meant that they required constant access to abundant prey species. Any disruption to the herbivore populations that supported them would quickly cascade through the entire ecosystem. Recent analysis of the ecological relationships in late Cretaceous ecosystems has revealed that they were characterized by what ecologists call tight coupling, high levels of interdependence between species that made the entire system vulnerable to cascading failure if any key components were disrupted. The very sophistication that made these ecosystems so successful also made them fragile. The complex behaviors, specialized relationships, and highly evolved adaptations that characterized late Cretaceous communities required stable environmental conditions to maintain. Any significant environmental disruption would threaten not just individual species, but the entire ecological framework that supported them. And yet, even as these ultimate predatory ecosystems were reaching their peak of success and sophistication, forces were building that would test their resilience in ways that no ecosystem had ever been tested before. The stage was being set for a catastrophe that would end not just individual species or communities, but an entire evolutionary era. Recent geological evidence has revealed that the late Cretaceous world was already experiencing environmental stresses that were beginning to challenge even these highly successful ecosystems. Climate change, sea level fluctuations, and volcanic activity were creating conditions that would have been difficult for any ecosystem to navigate, regardless of how well adapted or sophisticated it might have been. The final dinosaur predators were about to face the ultimate test of evolutionary success. Not competition from other predators or prey, not gradual environmental change that could be adapted to over-geological time, but sudden, catastrophic disruption that would challenge the very foundations of terrestrial life. So the question remains, if these ultimate predatory ecosystems represented the pinnacle of what terrestrial evolution could achieve, what lessons would their sudden destruction teach us about the relationship between evolutionary success and survival? And what opportunities would their disappearance create for entirely different forms of life to inherit the Earth? Chapter 17: The Ultimate Apocalypse. When the skies fell upon the giants, around 66 million years ago, something happened that would end the most successful predatory dynasty in Earth's history and fundamentally alter the trajectory of life on our planet forever. It wasn't gradual climate change, competitive displacement, or evolutionary obsolescence that brought down the dinosaur predators. It was a catastrophe so sudden, so complete, and so devastating that it redefined our understanding of how quickly evolutionary success can be transformed into extinction. There is a moment preserved in rock formations around the world that captures the instant when the Cretaceous period ended and the age of mammals began. In places like the Hell Creek Formation in Montana, the Ojo Alamo Formation in New Mexico, and similar deposits on every continent, geologists have found a thin layer of clay that marks one of the most significant moments in Earth's history, the day the dinosaurs died. It is strange to imagine, but this boundary layer, often no thicker than a few centimeters, contains the compressed story of a global catastrophe that unfolded over hours and days rather than millions of years. Within this narrow band of rock, we find evidence of wildfires that burned across continents, tsunamis that swept inland for hundreds of kilometers, and environmental changes so rapid and severe that they challenged the survival limits of virtually every large organism on Earth. The evidence for what happened 66 million years ago reads like a disaster movie script, but it was all terrifyingly real. Recent research has revealed that a massive asteroid, roughly 10 kilometers in diameter and traveling at speeds exceeding 20 kilometers per second, struck Earth with the force of billions of nuclear weapons. The impact site, now known as the Chicxulub crater, beneath the Yucatan Peninsula of Mexico, was ground zero for a catastrophe that would reshape the planet. Recent analysis of impact deposits around the world has revealed the sequence of events that followed the asteroid impact with remarkable precision. Within minutes of impact, massive earthquakes with magnitudes exceeding anything in recorded history shook the entire planet. Within hours, debris from the impact site was raining down across North America, igniting wildfires that consumed entire ecosystems. But here's the twist that makes this catastrophe even more devastating than the immediate impact effects. The asteroid strike triggered a cascade of environmental changes that continued for months and years after the initial impact. The debris ejected into the atmosphere blocked sunlight across the globe, creating what scientists call impact winter, a period of darkness and cold that lasted for months. Recent climate modelling has revealed that global temperatures dropped by as much as 30 degrees Celsius in some regions. Photosynthesis essentially stopped across most of the planet as sunlight levels dropped to less than 1% of normal. The entire foundation of terrestrial and marine ecosystems, the primary productivity that supported all food webs, collapsed within weeks of the impact. The reveal is that this catastrophe didn't just kill individual organisms or even individual species. It destroyed the ecological relationships that had supported complex life for over 160 million years. The sophisticated predator-prey dynamics, the complex social behaviors, and the efficient energy transfer systems that had characterized Cretaceous ecosystems all collapsed simultaneously. We cannot know for certain what it was like to experience this apocalypse, but the geological evidence suggests it was unlike any catastrophe that complex life had ever faced. Unlike previous extinction events that had unfolded over thousands or millions of years, allowing some organisms time to adapt or migrate, the end Cretaceous extinction happened so quickly that adaptation was impossible. Recent analysis of plant fossil assemblages from boundary layers around the world has revealed that forest ecosystems collapsed within weeks of the impact. The fern spikes found in post-impact deposits suggest that entire continents were reduced to landscapes resembling those found after massive volcanic eruptions, barren, ash-covered wastelands where only the hardiest pioneer species could survive. For the giant predatory dinosaurs that had ruled terrestrial ecosystems for over 160 million years, this environmental collapse was catastrophic. Their enormous size and high metabolic demands made them completely dependent on abundant prey species and stable food webs. When the herbivore populations that supported them collapsed, the predators followed within months. Recent research has revealed that the extinction of large dinosaurs wasn't just due to direct environmental effects, it was the result of ecosystem collapse that eliminated their food sources. Even if individual large dinosaurs could have survived the immediate environmental effects of the impact, they couldn't survive in a world where the ecological relationships that supported them no longer existed. The fossil record from immediately after the impact tells a story of ecological devastation that is difficult to comprehend. Recent analysis of earliest Paleocene fossil assemblages shows that terrestrial ecosystems were reduced to communities of small organisms, mostly mammals, birds, reptiles and amphibians weighing less than a few kilograms, that could survive on limited resources in simplified food webs. But perhaps most remarkably, this catastrophic destruction of existing ecosystems created opportunities for evolutionary innovations that had been impossible in the dinosaur-dominated world. The small mammals that survived the extinction were suddenly living in a world without large predators, where ecological niches that had been filled by dinosaurs for over 160 million years were suddenly vacant. Recent analysis of early mammalian evolution following the extinction has revealed rates of evolutionary change that were unprecedented in vertebrate history. Within just a few million years of the extinction, mammals had diversified from small generalized forms into ecological roles that had never been filled by mammalian species: large herbivores, specialized carnivores, and even early forms that would eventually lead to primates and human ancestors. The honest answer is that the asteroid impact that ended the age of dinosaurs was simultaneously the most devastating extinction event that complex terrestrial life had ever experienced, and the most important evolutionary opportunity in mammalian history. It was both an ending and a beginning on a scale that is difficult to comprehend. Recent research has revealed that this extinction event was so complete that it essentially reset terrestrial evolution. The ecological relationships, behavioral adaptations, and evolutionary trajectories that had characterized terrestrial life for over 160 million years were replaced by entirely new forms of organization based on different principles and different evolutionary possibilities. The haunting question is, what does this ultimate catastrophe teach us about the relationship between evolutionary success and survival? The dinosaur predators that were eliminated by the asteroid impact had been among the most successful organisms in Earth's history, yet their very success made them vulnerable to catastrophic change. Their large size, specialized adaptations, and complex ecological relationships, the very traits that had made them so successful for so long, became liabilities when faced with environmental changes that happened too quickly for evolutionary adaptation. The small, generalized mammals that survived were successful not because they were superior organisms, but because they were adaptable to catastrophic change. Recent analysis of extinction patterns across the end Cretaceous boundary has revealed that survival was largely determined by factors that had little to do with evolutionary sophistication or ecological success under normal conditions. Small size, behavioral flexibility, and the ability to survive on limited resources were far more important than intelligence, specialization, or predatory efficiency. And yet, the legacy of the dinosaur predators lives on in ways that continue to influence ecosystems today. The birds that survived the extinction are direct descendants of theropod dinosaurs, carrying forward many of the behavioral and physiological innovations that had made dinosaur predators so successful. Modern ecosystems still bear the imprint of over 160 million years of dinosaur evolution. The catastrophe that ended the age of dinosaurs was also the beginning of the age of mammals, the evolutionary radiation that would eventually lead to human consciousness and our ability to contemplate the deep history of life on Earth, reflective closure. And so we arrive at the end of our journey through Earth's most terrifying chapters, a journey that has taken us from toxic atmospheres that would have killed us instantly, through the rise of cellular monsters, the birth of intelligence, the emergence of coordinated hunting, the engineering of death traps, the invasion of land, the reign of giants, and finally, the dawn of vertebrate dominance. It is strange to imagine that all of this horror, all of this violence, all of this prehistoric terror was necessary to create the world we inhabit today. Every breath you take, every step you walk, every moment of safety you experience exists because countless organisms endured unimaginable dangers across billions of years of evolutionary time. The haunting question that lingers is this: were we wrong to call these ancient worlds terrifying? Or is terror simply the price that life pays for complexity, intelligence, and ultimately consciousness itself? We cannot know for certain, but perhaps the real lesson of these ancient horrors isn't about fear at all. Perhaps it's about resilience, adaptation, and the extraordinary capacity of life to not just survive, but to transform catastrophe into opportunity, extinction into innovation, and terror into the foundation for something beautiful. Thank you, fellow Sapiens, for joining me on this journey through deep time. If this helped you fall asleep, helped you study, or simply satisfied your curiosity about the incredible story that led to your existence, then we've shared something meaningful together. The honest answer is that we are all descendants of survivors, organisms that faced unimaginable dangers and somehow found ways to persist, to adapt, and to pass their resilience on to the next generation. That resilience lives within you, carries you forward, and connects you to every living thing that has ever existed. Stay curious, stay calm, and remember that you are the inheritor of the most extraordinary survival story ever told.